Today, we're diving into one of the biggest mysteries in space science, the Great Attractor. This is a cosmic detective story that starts with a simple question. Why are galaxies moving where they're moving? What astronomers discovered shocked them to their core. Our entire neighborhood of galaxies is being pulled towards something invisible, something so massive it defies explanation. And the craziest part? We're heading straight for it at over 2 million kilometers per hour. Back in the 1970s, astronomers thought they had the universe figured out. Galaxies were moving apart due to the Big Bang, right? Well, yes, but that's only part of the story. A team of researchers, led by astronomer Alan Dressler, was studying the motion of galaxies when they noticed something strange, very strange. Galaxies weren't just moving away from us uniformly. Some were moving toward us, others away, but not in the patterns anyone expected. It was like watching cars on a highway and realizing they're all drifting toward the same exit, even though they started in different lanes. This shouldn't happen if the universe is expanding evenly. Dressler and his team mapped hundreds of galaxies, measuring their speed and direction. They used something called redshift. When objects move away from us, their light stretches toward the red end of the spectrum. The more redshifted the light, the faster the object is moving away. But what they found made no sense. Our local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, wasn't just moving with the general expansion of the universe. We were all being pulled in a specific direction. Toward what? That was the million-dollar question. The team published their findings in 1987, and the astronomical community went wild. How could this be? What could possibly be pulling entire clusters of galaxies across hundreds of millions of light-years? The force needed would have to be enormous, equivalent to tens of thousands of galaxies like our Milky Way. This discovery kicked off a cosmic treasure hunt. Astronomers around the world pointed their telescopes toward this mysterious region of space, trying to see what was there. But here's where it gets really weird. When they looked in the direction we're all moving, they didn't see much of anything, just some normal galaxy clusters. Nothing that could explain such a massive gravitational pull. The region they were looking at is in the direction of the constellations Centaurus and Hydra, but it's hidden behind the plane of our own galaxy. The Milky Way's thick disk of stars, gas, and dust blocks our view, like trying to see through a foggy window. This zone of avoidance makes observations incredibly difficult. So astronomers got creative. They started using different wavelengths of light that could penetrate the dust. Infrared, radio waves, X-rays. Each new observation technique revealed a little more, but the full picture remained elusive. What they did find was a complex structure called the Norma cluster, also known as ACO 3627. This is a massive cluster of galaxies, but even at 10,000 trillion times the mass of our Sun, it wasn't big enough to explain the gravitational pull they were measuring. There had to be something else. Then came another twist. As technology improved and astronomers mapped more of the universe, they realized the Great Attractor might not be a single object at all. Instead, it could be the center of an even larger structure called the Laniakea supercluster. Let me explain what a supercluster is. Galaxies form groups, like our local group. These groups form clusters, which then form superclusters. The Laniakea supercluster contains about 100,000 galaxies, including our Milky Way, and spans 500 million light-years. And we're all moving toward a point called the Great Attractor, which seems to be the gravitational center of this supercluster. But here's the mind-bending part. Even the Laniakea supercluster is being pulled towards something even larger. Recent studies suggest that the Shapley supercluster, located about 650 million light-years away, might be influencing the motion of Laniakea. And beyond that, we don't know yet. It's like cosmic Russian dolls, with each layer revealing a larger structure pulling on the one before it. So what exactly is the Great Attractor? The honest answer is, we're still not sure. It's not a single object like a black hole or a galaxy cluster. It appears to be a gravitational focal point, a region where the density of matter is higher than average, creating a gravitational well that galaxies are falling into. One theory suggests it could be a massive dark matter concentration. Dark matter is the invisible stuff that makes up about 27% of the universe. We can't see it, but we know it's there because of its gravitational effects on visible matter. If there's an unusually large amount of dark matter in one region, it could create the gravitational pull we're observing. Another possibility is that the Great Attractor is a complex network of galaxy clusters and dark matter filaments. The universe isn't evenly distributed. It's more like a cosmic web, with galaxies strung along filaments of dark matter and vast voids in between. The Great Attractor might be where several of these filaments intersect, creating a region of higher density. What makes this mystery even more fascinating is that we're part of the story. Our Milky Way galaxy, along with everything in it, is being pulled toward this unseen force at breakneck speed. Every second, we're moving about 600 kilometers closer to it. Over millions of years, this adds up to enormous distances. But don't worry, we're not going to crash into it anytime soon. The universe is expanding, and while we're moving toward the Great Attractor, the space between us and it is also expanding. It's like walking up a down escalator. You're making progress, but slowly. The discovery of the Great Attractor changed our understanding of the universe. Before this, we thought of the universe as relatively uniform, with galaxies evenly distributed and moving apart due to cosmic expansion. Now we know it's much more complex, with vast structures and flows that we're only beginning to map. This discovery also highlights how much we still don't know about the universe. Dark matter, dark energy, cosmic flows, these are all areas where our understanding is still evolving. Each new discovery, like the Great Attractor, opens up new questions and new avenues of research. Astronomers are now working on creating more detailed maps of the universe, using new telescopes and observation techniques. The European Space Agency's Gaia satellite, for example, is precisely measuring the positions and movements of billions of stars in our galaxy, which helps us better understand our own motion through space. Other projects, like the Dark Energy Survey, are mapping millions of galaxies to better understand the large-scale structure of the universe. Each new piece of data brings us closer to solving the mystery of the Great Attractor. But perhaps the most exciting aspect of this discovery is what it tells us about our place in the universe. We're not just floating in empty space. We're part of a vast, dynamic cosmic structure, moving in ways we're only beginning to understand. Our galaxy is on a journey, and the Great Attractor is our destination, even if it's one we'll never reach in our lifetime. The story of the Great Attractor is a perfect example of how science works. It starts with an observation that doesn't fit our current understanding. Then comes the detective work, the hypothesis testing, the technological innovation, and finally, the new understanding that changes how we see the universe. And this story isn't over yet. As our technology improves and our maps become more detailed, we'll likely discover even larger structures influencing the motion of the Great Attractor itself. Each discovery leads to new questions, and each new question pushes us forward in our quest to understand the cosmos. The universe is full of mysteries, like the Great Attractor, phenomena that challenge our understanding and push the boundaries of human knowledge. And that's what makes astronomy so exciting. Every time we look up at the night sky, we're reminded of how much we still have to learn. So the next time you're outside on a clear night, look up at the stars and remember, everything you see, including our own galaxy, is on a journey towards something we can't even see. We're all being pulled by the Great Attractor, a hidden force that reminds us of how much wonder. So astronomers had this massive problem on their hands. Galaxies weren't behaving like they should. According to everything we knew about the expanding universe, galaxies should be moving away from each other in a pretty uniform way. But that's not what Dressler's team found. Instead, they saw this weird drift, like rivers of galaxies all flowing towards some invisible point in space. What could possibly explain this? Scientists started throwing out theories. each one more mind-bending than the last. First, they thought maybe there was something wrong with their measurements. After all, measuring the speed and direction of galaxies hundreds of millions of light years away is incredibly tricky. You're basically looking at tiny shifts in light that left those galaxies before dinosaurs even walked the Earth. So they double-checked, triple-checked, used different telescopes, different methods, but the results kept coming back the same. Something was definitely pulling these galaxies. Then came the theory of great walls, enormous sheet-like structures of galaxies that might be influencing motion. Astronomers had discovered these cosmic walls before, vast collections of galaxies stretching across hundreds of millions of light years. Maybe one of these walls was creating a gravitational pull, but when they calculated the mass needed, it still didn't add up. Even the biggest known structures weren't massive enough to explain the force they were seeing. Another idea was that maybe there was a super dense cluster hiding behind the Milky Way. Remember how I mentioned the zone of avoidance, that thick band of stars and dust that blocks our view? Well, what if something huge was lurking back there, invisible to our telescopes? Astronomers started using radio waves and X-rays to peer through the dust, hoping to catch a glimpse of what might be hiding. And they did find some galaxy clusters back there, like the Norma cluster I mentioned earlier. But again, not big enough, not nearly big enough. The more they looked, the more puzzled they became. Some scientists even suggested maybe our understanding of gravity was wrong on cosmic scales. That would be huge. Einstein's theory of general relativity has been incredibly successful, but perhaps it needed tweaking when applied to the entire universe. This led to all sorts of complex mathematical models trying to modify gravity to explain what they were seeing. But none of these models really worked without creating new problems elsewhere. Then there was the dark matter angle. We've known about dark matter for decades, this mysterious, invisible stuff that makes up about 27% of the universe. We can't see it, but we know it's there because of how it affects visible matter through gravity. Maybe there was an unusually large concentration of dark matter in that region. This seemed promising because dark matter doesn't emit light, making it very hard to detect. But even then, the amount needed would be staggering, like a mountain of dark matter the size of a supercluster. Astronomers started mapping the distribution of galaxies more carefully, looking for patterns. They noticed that galaxies weren't just moving toward one point. They were flowing like water, following these cosmic currents. It was like discovering rivers in space, with galaxies flowing along invisible channels. This suggested that whatever was causing this motion wasn't a single object, but perhaps a complex gravitational landscape with hills and valleys made of dark matter. The technology kept getting better. New telescopes came online. New observation techniques were developed. Astronomers started using something called peculiar velocity measurements. That's the motion of galaxies beyond the general expansion of the universe. By carefully measuring these peculiar velocities, they could create maps of how galaxies were moving relative to each other. And these maps showed something incredible. Vast flows of galaxies, some stretching across hundreds of millions of light years, all converging toward the same general region. One of the most important discoveries came from a team led by Sandra Faber and Donald Lyndon Bell. They were studying the motions of elliptical galaxies, these big, blob-shaped galaxies that are often found at the centers of galaxy clusters. What they found was that these elliptical galaxies were all moving in the same direction, toward the same spot in the sky. This was independent confirmation that something massive was out there, pulling everything toward it. But here's where it gets really interesting. As astronomers mapped more and more of the universe, they realized that the Great Attractor wasn't acting alone. It seemed to be part of an even larger structure. Galaxies were flowing toward the Great Attractor, but the Great Attractor itself appeared to be moving toward something else. It was like discovering that the river flows into a lake, but that lake itself is flowing toward an ocean. This led to the concept of cosmic flows, these massive movements of matter on the largest scales of the universe. The Great Attractor wasn't just some local anomaly, it was part of a pattern, a vast network of gravitational influences stretching across the observable universe. Astronomers realized they weren't just studying one mystery, They were uncovering the hidden architecture of the cosmos itself. The early attempts to explain the unusual galaxy motions really showed the scientific process in action. Scientists observed something unexpected, proposed theories, tested them, discarded what didn't work, and gradually built up a picture of what might be happening. It was messy, frustrating, and exciting, all at the same time. Each new discovery raised as many questions as it answered. What they were beginning to understand was that the universe isn't just expanding uniformly. It's got this complex internal structure, with vast regions where matter is clumped together, creating gravitational wells that influence everything around them. The Great Attractor appeared to be one of the most significant of these regions, a focal point where multiple cosmic flows converged. But even with all this progress, the fundamental mystery remained. What exactly was the Great Attractor? Was it a single object, a cluster of objects, a concentration of dark matter, or something else entirely that we hadn't even thought of yet? The more they learned, the more they realized how much they still didn't know. This period of cosmic puzzle solving set the stage for the next phase of discovery. With better technology and more sophisticated mapping techniques, astronomers were about to uncover something even more mind-blowing than they could have imagined. The Great Attractor was just the beginning, the visible tip of a cosmic iceberg that would change our understanding of the universe forever. The story of how they finally pieced together the full picture is incredible, involving new telescopes, international collaborations, and some of the most ambitious mapping projects ever undertaken. But that's a story for our next chapter. For now, just remember, when scientists first noticed galaxies moving in strange ways, they had no idea they were stumbling upon one of the largest structures in the universe, a hidden force pulling galaxies across hundreds of millions of light years, and we're all caught in its pull. If you want to see how this cosmic mystery unfolds, watch our next video, where we reveal what astronomers found when they finally mapped the Great Attractor in detail. Imagine trying to see a mountain range right in front of you, but there's a thick fog blocking your view. That's exactly the problem astronomers faced when trying to solve the mystery of the Great Attractor. Right in the direction where all these galaxies were heading, smack in the middle of the constellations Centaurus and Hydra, sits our own Milky Way galaxy. And our galaxy, beautiful as it is, became a giant curtain hiding the cosmic show behind it. This region is called the Zone of Avoidance, and it's one of the biggest headaches in astronomy. Here's why. Our Milky Way is shaped like a flat disk, with spiral arms swirling out from a bright center. We live inside this disk, about halfway from the center to the edge. When we look out toward the edges of the disk, we're looking through a lot of stuff: stars, gas clouds, and most importantly, thick clouds of interstellar dust. This dust is like cosmic smoke. It doesn't emit light, and it absorbs or scatters the light from objects behind it. So when astronomers tried to look toward the Great Attractor, they were essentially trying to peer through a wall of cosmic fog. Think of it like this. If you're in a room filled with smoke, you can't see what's on the other side. The smoke blocks your view. That's exactly what the dust in our galaxy does. It blocks about 20% of the entire night sky from our view. And guess what? The Great Attractor sits right in the middle of that blocked region. What are the odds, right? It's like the universe played a cosmic prank on us, hiding one of its biggest mysteries right behind our own backyard. This dust isn't just a thin layer. It's incredibly thick and dense in some places. The dust clouds are so effective at blocking light that even powerful telescopes like Hubble struggled to see through them. Visible light, the kind our eyes see, gets completely absorbed by these dust clouds. So astronomers couldn't just point their telescopes at the zone of avoidance and expect to see what was pulling all those galaxies. They had to get creative. But here's where human ingenuity comes in. Scientists realize that while the dust blocks visible light, it doesn't block all types of radiation. Different wavelengths of light behave differently when they hit dust clouds. Some can pass right through, while others get absorbed. So astronomers started using telescopes that could see these other types of light that our eyes can't see. First, they turned to radio waves. Radio telescopes, like the famous ones at the Very Large Array in New Mexico, can detect radio waves emitted by objects in space. These long waves pass right through dust clouds like they're not even there. By using radio telescopes, astronomers began mapping the hidden parts of the sky. What they found was surprising. There were galaxies back there, lots of them, but they were distorted and hard to see clearly. It was like looking through a frosted window. You know something's there, but you can't make out the details. Then came infrared telescopes. Infrared light has longer wavelengths than visible light, but shorter than radio waves. It's also really good at penetrating dust. Telescopes like NASA's Spitzer Space Telescope and the European Space Agency's Herschel Observatory were designed to see in infrared. When they pointed toward the zone of avoidance, they revealed even more galaxies and structures that were invisible in visible light. It was like putting on night vision goggles in a dark room. Suddenly, a whole new world appeared. X-ray telescopes joined the party too. Objects like galaxy clusters and black holes emit X-rays, which can also pass through dust. Telescopes like NASA's Chandra X-ray Observatory detected hot gas in galaxy clusters hidden behind the Milky Way's dust. This gas was superheated to millions of degrees, glowing brightly in X-rays, but completely invisible to optical telescopes. But even with all these tools, seeing through the zone of avoidance was like solving a giant jigsaw puzzle with half the pieces missing. Astronomers had to combine data from multiple telescopes using different wavelengths to build up a picture of what was back there. They used computer programs to layer radio maps, infrared images, and X-ray data, trying to create a complete picture of the hidden sky. One of the biggest breakthroughs came from a project called the 2MASS Redshift Survey. This survey used infrared telescopes to map the positions and distances of thousands of galaxies, including those in the zone of avoidance. What they found was a massive cluster of galaxies called the Norma Cluster, also known as ACO 3627. This cluster was huge, containing thousands of galaxies and weighing in at about 10,000 times the mass of our Milky Way. But here's the thing. Even this massive cluster wasn't big enough to explain the gravitational pull of the Great Attractor. It was like finding a big rock when you were looking for a mountain. The more astronomers looked, the more they realized the zone of avoidance wasn't just hiding one thing. It was hiding a complex network of galaxy clusters, superclusters, and dark matter filaments. Each new observation revealed more pieces of the puzzle, but the full picture remained frustratingly out of reach. It was like peeling an onion, layer by layer, only to find another layer underneath. The dust in our galaxy isn't evenly distributed either. Some parts of the zone of avoidance are thicker and more opaque than others. This created windows where astronomers could catch glimpses of what lay beyond. These windows became crucial observation points. By focusing on these clearer spots, astronomers could map structures behind the dust and then extrapolate what might be in the darker regions. Another challenge was that the dust itself emits light. It's faint, but it's there. This cirrus emission, as astronomers call it, can mimic the light from distant galaxies, creating false signals. Astronomers had to develop sophisticated techniques to separate the real signals from the dust noise. It was like trying to hear a whisper in a noisy room. You have to filter out all the background sounds to hear what you're looking for. The technology kept getting better. New telescopes came online with more sensitive detectors. Computer processing power increased, allowing astronomers to analyze massive amounts of data more quickly. Projects like the Herschel Space Observatory mapped the dust in our galaxy in unprecedented detail, creating a 3D map of where the thickest clouds were and where the clearer windows might be. But even with all this progress, the zone of avoidance remains one of the least explored regions of the nearby universe. We've made huge strides, but there's still so much we don't know. It's a humbling reminder of how limited our view of the cosmos really is. We like to think we've mapped everything, but right in our own cosmic backyard, there's a region we're still struggling to see clearly. The zone of avoidance also taught astronomers an important lesson about perspective. Our position inside the Milky Way gives us a unique view of the universe, but it also creates blind spots. It's like living in a house with windows on only one side. You can see out that side really well, but you have no idea what's happening on the other sides. This cosmic perspective problem is something astronomers always have to keep in mind. What makes the zone of avoidance even more fascinating is that it's not permanent. Our Milky Way is moving through space, and over millions of years, our position relative to the galactic disk will change. Eventually, the Great Attractor region won't be hidden behind the dust anymore. Of course, by then, the Great Attractor itself will have moved, and the cosmic landscape will look completely different. But it's a reminder that the universe is constantly changing, and what's hidden today might be revealed tomorrow. The struggle to see through the zone of avoidance really shows the detective nature of astronomy. Scientists are like cosmic detectives, following clues, overcoming obstacles, and slowly piecing together the puzzle of the universe. Every technological advance, every new telescope, every clever observation technique helps pull back another layer of the cosmic curtain. And the best part? We're living in a golden age of astronomy. New telescopes like the James Webb Space Telescope are already revolutionizing our view of the cosmos. With its powerful infrared vision, Webb is peering through dust clouds better than ever before, revealing galaxies and structures that were previously hidden. Who knows what mysteries it might uncover in the zone of avoidance? The story of the zone of avoidance isn't just about dust blocking our view. It's about human curiosity and ingenuity. It's about how we refuse to let obstacles stop us from understanding the universe. And it's a reminder that even in the age of advanced technology, there are still cosmic frontiers waiting to be explored. So next time you look up at the Milky Way, stretching across the night sky, remember that beautiful band of light is also a cosmic curtain. Behind it lies one of the universe's greatest mysteries, a hidden force pulling galaxies across hundreds of millions of light years. And astronomers, armed with ever more powerful tools, are slowly pulling back that curtain, revealing the secrets that lie beyond. Picture this. It's the late 1980s, and a group of astronomers is staring at maps of the universe that look like abstract art. These aren't just any maps. They're showing how thousands of galaxies are moving through space, and what they're seeing doesn't make any sense. Galaxies aren't just drifting apart like they should be after the Big Bang. They're flowing, like rivers, all heading toward one specific patch of sky. But when they look at that patch of sky, nothing, just empty space, or so it seemed. This was the moment they first realized something truly bizarre was happening out there. Something invisible, but incredibly powerful. Something they would later call the Great Attractor. Let's rewind a bit. In the 1970s, astronomers started using a new technique to map the universe in 3D. It's called redshift survey. Here's how it works. When a galaxy moves away from us, the light it emits stretches out, shifting toward the red end of the spectrum. The faster it's moving, the more the light shifts. By measuring this redshift, astronomers can figure out both the direction and speed of distant galaxies. It's like cosmic radar. A team led by astronomers Alan Dressler, Sandra Faber, Donald Lyndon Bell, and others decided to use this technique to map the motions of hundreds of elliptical galaxies. These big, blob-shaped galaxies are often found at the centers of galaxy clusters, making them good markers for large-scale movements. What they discovered blew their minds. Our local group of galaxies, that's the Milky Way, Andromeda, and about 50 smaller galaxies hanging out together, wasn't just moving with the general expansion of the universe. We were all being pulled sideways, hard, toward a specific region in the sky. And we weren't alone. Galaxies hundreds of millions of light years away were also being pulled in the same direction. It was like discovering that rivers all over the world are mysteriously flowing toward the same point on the map, even though that point isn't the lowest elevation. The team published their findings in 1987, and the astronomical community went into a frenzy. Here was this massive gravitational anomaly, something so powerful it could influence the motion of galaxies across hundreds of millions of light years. But when they pointed their telescopes at that region of space, they didn't see anything that could explain it. No supermassive black hole, No giant galaxy cluster, just empty space, or so it seemed. They named this mysterious gravitational focal point the Great Attractor, and what a name it was. It captured both the scale, great, and the effect, attractor. Something out there was attracting galaxies on a scale no one had ever imagined before. But here's where it gets really weird. The Great Attractor wasn't just pulling our local group. It was influencing the motion of entire galaxy clusters. The Virgo cluster, which is the big cluster of galaxies closest to us, about 50 million light-years away, also being pulled toward the Great Attractor. The Hydra Centaurus supercluster, same thing. It was like this invisible cosmic vacuum cleaner, sucking in everything around it. The numbers were staggering. Calculations showed that whatever was causing this pull had to have a mass equivalent to tens of thousands of galaxies, like our Milky Way. That's something like 10 quadrillion times the mass of our Sun. Let me put that in perspective. If you counted one star every second, it would take you over 300,000 years to count that many stars. And all that mass was concentrated in one region of space, a region that appeared completely empty. Astronomers were baffled. How could something so massive remain invisible? They started considering all sorts of possibilities. Maybe it was a supermassive black hole billions of times heavier than any we'd ever seen. But even the biggest black holes known at the time weren't nearly massive enough. Plus, black holes that big would probably be surrounded by bright accretion disks of superheated gas, which should be visible from Earth. Maybe it was a giant cluster of galaxies, hidden behind the Milky Way's dust. That seemed more plausible. Remember the zone of avoidance we talked about? The Great Attractor was located right in that obscured region, so perhaps there was a massive galaxy cluster back there, hidden from view. But when they used radio and infrared telescopes to peer through the dust, they didn't find anything big enough. They found some galaxy clusters, like the Norma cluster, but nothing that could explain the gravitational pull they were measuring. Another theory suggested it might be a concentration of dark matter. Dark matter is this mysterious, invisible stuff that makes up about 27% of the universe. We can't see it, but we know it's there because of its gravitational effects. Maybe there was an unusually large amount of dark matter in that region. This seemed promising because dark matter doesn't emit light, making it very hard to detect. But even then, the amount needed would be extraordinary. The discovery of the Great Attractor was a classic example of scientific detective work. Astronomers had observed something strange, galaxies moving in unexpected ways, proposed a hypothesis, something massive is pulling them, and then tested that hypothesis by looking for evidence. But the evidence wasn't adding up. Whatever was causing the gravitational pull remained stubbornly invisible. What made this discovery even more significant was that it challenged our understanding of the universe on the largest scales. Before this, astronomers thought of the universe as relatively uniform, with galaxies evenly distributed and moving apart due to cosmic expansion. The Great Attractor showed that the universe has a complex internal structure, with vast regions where matter is clumped together, creating gravitational wells that influence everything around them. The discovery also highlighted how much we still don't know about the universe. Here was something massive, something influencing the motion of entire clusters of galaxies, and we couldn't see it. It was a humbling reminder of the limits of our knowledge and our technology. But astronomers weren't about to give up. The discovery of the Great Attractor kicked off a new era of cosmic mapping. New telescopes were built, new observation techniques were developed, international collaborations were formed, all with one goal: to solve the mystery of the Great Attractor. One of the most important projects to come out of this was the 2 MASS redshift survey, which we mentioned earlier. This survey used infrared telescopes to map the positions and distances of thousands of galaxies, including those in the zone of avoidance. What they found was a complex network of galaxy clusters and superclusters, all interconnected by filaments of dark matter. The Great Attractor appeared to be at the center of this network, like the hub of a cosmic wheel. Another crucial project was the Cosmic Flows program, led by astronomer Brent Tully. This team mapped the motions of thousands of galaxies to create a 3D map of how matter is flowing in the nearby universe. Their maps showed vast rivers of galaxies flowing toward the Great Attractor, confirming and expanding on the earlier discoveries. But perhaps the most mind-blowing discovery came when astronomers realized that the Great Attractor itself was moving. It wasn't some fixed point in space. It was being pulled towards something even larger, something beyond the edge of what they had mapped so far. This suggested that the Great Attractor wasn't the final destination. It was just a waypoint on a much longer journey. The discovery of the Great Attractor was a pivotal moment in astronomy. It changed how we see the universe. It showed us that the cosmos is not just expanding uniformly, but has a complex internal structure with vast flows and currents. It revealed that there are massive structures out there that we can't see directly, but can detect through their gravitational effects. And it raised profound questions about the nature of the universe. What is the Great Attractor? Is it a single object or a collection of objects? How did it form? And what does it tell us about the distribution of matter in the universe? These questions drive astronomers to this day. New telescopes like the James Webb Space Telescope are peering deeper into the zone of avoidance than ever before. New mapping projects are creating ever more detailed 3D maps of the universe, and each new discovery brings us closer to solving the mystery of the Great Attractor. The story of the Great Attractor is far from over. In fact, it's just getting interesting. As we'll see in the next chapters, the Great Attractor is just one piece of a much larger cosmic puzzle, a puzzle that includes structures so vast they defy imagination, structures that are reshaping our understanding of the universe itself. If you want to uncover what astronomers found when they finally mapped the Great Attractor in detail, watch our next video where we reveal the hidden structure behind this cosmic mystery. By the early 1990s, astronomers had a cosmic problem on their hands. The evidence for the Great Attractor was overwhelming, like footprints in the sand proving something massive had walked by, but the something itself, nowhere to be found. It was like hearing thunder without seeing a storm, or feeling heat without a fire. The more they looked, the more the mystery deepened. Every new discovery seemed to raise more questions than it answered. Let me walk you through how this cosmic ghost hunt unfolded. First, let's talk about the tools astronomers were using. Technology was advancing fast. New telescopes, new detectors, new computer programs, all helping them map the universe in ways they never could before. One game changer was the Hubble Space Telescope, launched in 1990, orbiting above Earth's atmosphere. Hubble could see farther and clearer than any ground-based telescope, but even Hubble struggled with the zone of avoidance. That thick band of dust in our galaxy was still blocking the view. So astronomers got creative. They started using something called gravitational lensing. Here's how that works. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity of that object bends the light, acting like a lens. By studying how the light was bent, astronomers could map where the mass was, even if they couldn't see it directly. It's like seeing ripples in a pond and knowing something big dropped in, even if you didn't see the splash. When they applied this technique to the Great Attractor region, they found something strange. There was mass there, lots of it, but it wasn't concentrated in one spot. Instead, it was spread out in a complex web of dark matter and galaxy clusters. It was like finding a mountain range instead of a single mountain. But even this mountain range wasn't massive enough to explain the gravitational pull they were measuring. There had to be more. Then came the X-ray telescopes. Objects like galaxy clusters are filled with hot gas that glows brightly in X-rays. Telescopes like NASA's Chandra X-ray Observatory could detect this gas, revealing where the massive structures were hiding. When Chandra pointed toward the Great Attractor region, it found several galaxy clusters glowing in X-rays. These clusters were massive, each containing hundreds or thousands of galaxies. But again, when astronomers added up all the mass from these clusters, it still wasn't enough. It was like finding several large rocks when you were looking for a boulder. The more they mapped, the more complex the picture became. The Great Attractor wasn't a single object. It was a region, a vast area of space where matter was unusually dense. Within this region, there were galaxy clusters, superclusters, and vast clouds of dark matter, all interconnected by invisible filaments. It was like discovering that instead of one giant magnet pulling everything, there was a whole network of magnets working together. But here's where it gets really mind-bending. As astronomers mapped more of the universe, they realized that the Great Attractor itself was moving. It wasn't some fixed point in space. It was being pulled towards something even larger, something beyond the edge of what they had mapped so far. This was a huge revelation. It meant that the Great Attractor wasn't the final destination. It was just a waypoint on a much longer journey. Imagine you're in a river flowing toward the ocean. You think the ocean is your destination, but then you realize the ocean itself is flowing into something even larger, maybe a global current that circles the planet. That's what astronomers were discovering. The Great Attractor was like that ocean. Massive, but still part of something bigger. One of the most important projects to come out of this was the Cosmic Flows program, led by astronomer Brent Tully. His team mapped the motions of thousands of galaxies to create a 3D map of how matter is flowing in the nearby universe. Their maps showed something incredible. Galaxies weren't just flowing toward the Great Attractor. They were flowing in vast rivers, some stretching across hundreds of millions of light years, all converging toward the Great Attractor region. But beyond that, these rivers continued, flowing toward something even farther away. What was this something? Astronomers called it the Shapley Attractor, or the Shapley Supercluster. It's a massive concentration of galaxy clusters located about 650 million light-years away, and it's even more massive than the Great Attractor. The Shapley Supercluster contains thousands of galaxy clusters and has a mass equivalent to more than 10,000 Milky Way galaxies. It's one of the largest known structures in the universe. But here's the crazy part. Even the Shapley Supercluster might not be the final destination. Some astronomers think there could be something even larger beyond it. It's like cosmic Russian dolls, each layer revealing a larger structure pulling on the one before it. The universe, it turns out, has a complex internal structure that we're only beginning to map. The discovery that the Great Attractor was part of this larger flow changed everything. It meant that the gravitational anomaly wasn't just some local curiosity. It was part of the fundamental architecture of the universe. The cosmos isn't just expanding uniformly. It's got these vast flows and currents, like rivers in space, all influenced by the distribution of matter on the largest scales. But this raised even more questions. What was causing these flows? What was the ultimate source of all this gravitational pull? And why was the matter in the universe distributed this way? These questions pushed astronomers to develop new theories and new models of the universe. One theory suggested that these flows were remnants from the early universe. After the Big Bang, matter wasn't evenly distributed. There were slight variations in density. Some regions had a little more matter, others a little less. Over billions of years, gravity amplified these differences. The denser regions pulled in more matter, becoming even denser, while the less dense regions became emptier. Eventually, this created the cosmic web we see today. Vast filaments of matter connecting galaxy clusters and superclusters with enormous voids in between. The Great Attractor, according to this theory, is where several of these filaments intersect. It's a gravitational focal point where multiple cosmic rivers meet, but it's not the end of the journey. The rivers continue flowing toward even denser regions, like the Shapley supercluster. Another theory suggested that dark energy might be playing a role. Dark energy is this mysterious force that's causing the expansion of the universe to accelerate. Some astronomers think that dark energy might be influencing how matter clusters on the largest scales, creating these vast flows and attractors. But this is still highly speculative. We don't understand dark energy well enough to say for sure. What made the Great Attractor mystery even more frustrating was that every time astronomers thought they were getting close to solving it, new evidence would emerge that complicated the picture. It was like trying to solve a puzzle where someone kept adding new pieces. For example, in the early 2000s, astronomers using the 2MASS redshift survey discovered that the Milky Way and our neighboring galaxies weren't just moving toward the Great Attractor, we were also moving perpendicular to it, like a boat being pulled sideways in a river. This suggested that there were other gravitational influences at play, adding another layer of complexity to the picture. Then came the Planck satellite, launched by the European Space Agency in 2009. Planck was designed to map the cosmic microwave background, the faint afterglow of the Big Bang. By studying tiny variations in this background radiation, astronomers could create a map of the early universe and see how matter was distributed back then. What they found was that the distribution of matter in the early universe matched the large-scale structures we see today, including the Great Attractor region. This suggested that the seeds of the Great Attractor were planted just 400,000 years after the Big Bang. But even this discovery didn't solve the mystery. It just pushed it back in time. If the Great Attractor was already forming in the early universe, what caused that initial concentration of matter? And how did it grow into the massive structure we see today? The more astronomers learned, the more they realized that the Great Attractor wasn't just one thing. It was a complex system with multiple components. There was the Norma cluster, a massive galaxy cluster at the center of the Great Attractor region. There were other galaxy clusters nearby, all interconnected by filaments of dark matter. And there was the influence of even larger structures like the Shapley supercluster. It was like discovering that what you thought was a single mountain was actually a whole mountain range, connected by valleys and ridges, all part of a larger continental divide. The Great Attractor wasn't a face, it was a landscape. This realization changed how astronomers studied the Great Attractor. Instead of looking for a single massive object, they started mapping the entire region in detail. They wanted to understand how all the components fit together: the galaxy clusters, the dark matter filaments, the flows of galaxies. It was like shifting from studying a single tree to studying the entire forest. One of the most important tools in this effort was computer simulation. Astronomers created massive computer models of the universe, simulating how matter evolved from the Big Bang to the present day. These simulations could reproduce the cosmic web, the filaments, the voids, the clusters, and they showed that structures like the Great Attractor were natural outcomes of how gravity works on cosmic scales. But even these simulations couldn't explain everything. The Great Attractor region was more complex than the models predicted. It had more mass, more structure, more everything. It was like the universe was playing by rules we didn't fully understand. The mystery deepened even further when astronomers started measuring the peculiar velocities of galaxies. That's the motion of galaxies beyond the general expansion of the universe. What they found was that galaxies weren't just flowing toward the Great Attractor. They were flowing in complex patterns, like eddies in a river. Some galaxies were moving faster than expected, others slower. Some were even moving in unexpected directions. These peculiar velocities suggested that the gravitational landscape was even more complex than we thought. There were hills and valleys of gravity that we hadn't mapped yet. It was like discovering that the river had underwater currents we couldn't see from the surface. By the mid-2000s, astronomers had amassed an incredible amount of data about the Great Attractor. They had mapped thousands of galaxies, measured their motions, detected hot gas in X-rays, mapped dark matter through gravitational lensing, and run massive computer simulations. And yet, the fundamental mystery remained. What exactly was the Great Attractor, and why was it so hard to see? Part of the problem was that the Great Attractor wasn't a single object with clear boundaries. It was a region, a vast area of space where the gravitational pull was stronger than average. Defining exactly where it began and ended was like trying to define where a mountain range begins and ends. There's no clear line. Another problem was that we're inside the system. Our Milky Way galaxy is being pulled toward the Great Attractor, along with everything else. It's like trying to study a river while floating in it. You can see the water flowing around you, but it's hard to get the big picture. The more astronomers studied the Great Attractor, the more they realized that it wasn't just a mystery about one part of the universe. It was a mystery about the universe itself. How did matter get distributed this way? What forces shape the cosmic web? And what does this tell us about the fundamental laws of physics? These questions drive astronomers to this day. New telescopes like the James Webb Space Telescope are peering deeper into the zone of avoidance than ever before. New mapping projects are creating ever more detailed 3D maps of the universe, and each new discovery brings us closer to solving the mystery of the Great Attractor. But here's the thing about cosmic mysteries. Sometimes solving them just reveals deeper mysteries. The Great Attractor might turn out to be just one piece of an even larger cosmic puzzle, a puzzle that includes structures so vast they defy imagination, structures that are reshaping our understanding of the universe itself. The Great Attractor remains a force without a face, a gravitational ghost that haunts our maps of the cosmos. But it's not just a mystery, it's a window into the hidden architecture of the universe. And every time we look through that window, we see something new, something unexpected, something that challenges what we thought we knew. That's the beauty of astronomy. It's not just about finding answers, it's about asking better questions. And the Great Attractor has given us some of the best questions in cosmology, questions that will keep astronomers busy for decades to come. If you want to see how astronomers finally mapped the Great Attractor in detail and discovered the hidden structure behind this cosmic mystery, watch our next video, where we reveal the full picture of this incredible cosmic phenomenon. Imagine you're floating down a river, but you don't even know the river exists. You feel the current pulling you, but you can't see it. You're moving, but you don't know why. That's exactly what's happening to our Milky Way galaxy right now. We're caught in a cosmic current so powerful, it's sweeping our entire neighborhood of galaxies across the universe at breakneck speed. And until recently, we had no idea. Today, we're uncovering how our galactic family, the local group, is being pulled by an invisible force toward a destination we'll never reach in our lifetime. Let's start with something mind-blowing. Our Milky Way isn't sitting still in space. It's moving fast. About 600 kilometers every second. That's over 2 million kilometers per hour. To put that in perspective, if you could drive that speed, you could circle the Earth's equator 50 times in just 1 hour. But where are we going? And why? That's where the local group comes in. The local group is our cosmic neighborhood. It's a collection of about 80 galaxies held together by gravity. Think of it like a small town in the cosmic countryside. The big shots in this town are 3 spiral galaxies. Our Milky Way, the Andromeda Galaxy, also called M31, and the Triangulum Galaxy, M33. Andromeda is actually bigger than the Milky Way, about 220,000 light-years across, compared to our 100,000 light-years. Triangulum is smaller, about half our size. Then there are dozens of smaller galaxies, mostly dwarf galaxies, orbiting these big ones. The 2 most famous are the Large and Small Magellanic Clouds, satellite galaxies of the Milky Way that you can see from the southern hemisphere. For decades, astronomers thought these galaxies were just orbiting each other in a relatively stable dance. The Milky Way and Andromeda are actually moving toward each other, destined to collide in about 4.5 billion years. But that's just the local traffic. What astronomers discovered in the 1980s changed everything. Our entire local group isn't just doing its own thing. It's being swept along by a much larger current. Here's how they figured it out. Astronomers use something called redshift to measure how galaxies are moving. When a galaxy moves away from us, the light it emits stretches out, shifting toward the red end of the spectrum. When it moves toward us, the light compresses, shifting toward blue. By measuring these shifts, astronomers can calculate both the speed and direction of distant galaxies. When they measured the motion of galaxies in the local group, they noticed something strange. All of them, the Milky Way, Andromeda, Triangulum, And even the dwarf galaxies were moving in the same general direction, not just orbiting each other, but all drifting together toward a specific point in space. It was like discovering that all the cars in your town aren't just driving around locally, they're all being carried by a massive river current toward the same distant city. The numbers were staggering. The entire local group is moving toward the Great Attractor region at about 600 kilometers per second. That's faster than Earth orbits the Sun, faster than the Sun orbits the center of the Milky Way. We're talking about a speed that would get you from Earth to the Moon in just 10 minutes. And we're all moving together. The Milky Way, Andromeda, Triangulum, and all the smaller galaxies, like leaves caught in a cosmic stream. But here's where it gets really interesting. Each galaxy in the local group has its own peculiar velocity. That's the motion it has beyond the general flow. For example, Andromeda is moving toward the Milky Way at about 110 kilometers per second because of their mutual gravitational attraction. But both galaxies are also being swept along by the larger flow toward the Great Attractor. It's like two people dancing while standing on a moving walkway. They're moving relative to each other, but they're both being carried in the same direction by the walkway. Astronomers mapped these motions in incredible detail. They found that the dwarf galaxies orbiting the Milky Way, like the Magellanic Clouds, are also caught in this flow. Even though they're gravitationally bound to the Milky Way, they're still being swept along with everything else. It's like a flock of birds flying together while being carried by the wind. The birds are moving relative to each other, but the whole flock is moving in the same direction. What's even more amazing is that this flow isn't just affecting the local group. It's affecting entire clusters of galaxies around us. The Virgo cluster, which is the big cluster of galaxies closest to us, about 50 million light-years away, is also being pulled toward the Great Attractor. So is the Fornax cluster and the Centaurus A group. It's like discovering that not just your town, but all the neighboring towns are being swept along by the same river current. The scale of this motion is hard to comprehend. We're not just talking about galaxies moving through space. We're talking about entire clusters of galaxies, each containing hundreds or thousands of galaxies, all flowing in the same direction. The local group is just a tiny part of this much larger flow. It's like a single drop of water in a massive river. But how do astronomers know this? How can they measure something so vast? The answer lies in something called the cosmic distance ladder. Astronomers use a series of techniques to measure distances to galaxies, starting with nearby objects and working their way out. For nearby galaxies, they use Cepheid variable stars that pulse at a rate related to their brightness. By measuring how bright these stars appear from Earth, astronomers can calculate how far away they are. For more distant galaxies, they use Type 1a supernovae, exploding stars that have a consistent brightness. By measuring how bright these supernovae appear, astronomers can calculate their distance. And by measuring the redshift of these galaxies, they can calculate how fast they're moving away from us due to the expansion of the universe. But here's the clever part. By comparing the actual motion of galaxies, their peculiar velocity, with the motion expected from cosmic expansion, astronomers can figure out if they're being pulled by something else. If a galaxy is moving faster away from us than expected, or in a different direction, that means something is pulling it. And when they did this calculation for galaxies in our cosmic neighborhood, they found that all of them were being pulled toward the Great Attractor region. The more they mapped, the clearer the picture became. The local group isn't just moving randomly through space. It's part of a vast flow of galaxies, a river of matter flowing toward the Great Attractor. This flow includes not just the local group, but the Virgo cluster, the Fornax cluster, and many other galaxy groups and clusters. Together, they form what astronomers call the local sheet, a flat arrangement of galaxies all moving together. What's really fascinating is that this flow isn't smooth. It's more like a turbulent river with eddies and currents. Some galaxies are moving faster than others. Some are moving in slightly different directions. But overall, the general flow is clear. Everything is moving toward the Great Attractor. One of the most detailed studies of this flow came from the Cosmic Flows project, led by astronomer Brent Tully. His team mapped the motions of over 8,000 galaxies to create a 3D map of how matter is flowing in the nearby universe. What they found was incredible. The local group is part of a vast flow that extends hundreds of millions of light years. Galaxies are flowing like water in a river, all converging toward the Great Attractor region. But here's the mind-bending part. Even as we're being pulled toward the Great Attractor, the universe is expanding. The space between us and the Great Attractor is getting larger. It's like walking up a down escalator. You're making progress, but slowly. That's why we'll never actually reach the Great Attractor. The expansion of the universe will keep us apart, even as gravity pulls us together. The discovery of this flow changed our understanding of the universe. Before this, we thought of galaxies as relatively fixed objects, moving apart due to cosmic expansion. Now we know that on smaller scales, galaxies are flowing in complex patterns, influenced by the distribution of matter around them. The universe isn't just expanding uniformly. It's got this complex internal structure with vast flows and currents. The flow of the local group toward the Great Attractor is a perfect example of this. It shows that our cosmic neighborhood isn't isolated. We're part of a much larger system, influenced by forces on scales we're only beginning to understand. Our Milky Way galaxy, our solar system, our planet. We're all caught in this cosmic current, swept along by an invisible force toward a destination we'll never reach. But what does this mean for us? On a human scale, not much. The forces involved are so vast, and the timescales so long, that they don't affect our daily lives. But on a cosmic scale, it's profound. It means we're part of something much bigger than ourselves. We're not just floating in empty space. We're on a journey that began billions of years ago and will continue for billions more. The flow of the local group toward the Great Attractor is a reminder of how dynamic the universe is. It's not static. It's constantly changing, evolving, moving. Galaxies aren't just sitting there. They're dancing, flowing, being pulled by invisible forces across the cosmos, and we're part of that dance. As we continue to map the universe, we're discovering more and more about these cosmic flows. We're learning how galaxies move, how they interact, how they're influenced by the large-scale structure of the universe, and each new discovery brings us closer to understanding our place in the cosmos. The flow of the local group toward the Great Attractor is just one piece of this cosmic puzzle, but it's a crucial piece. It shows us that our cosmic neighborhood isn't isolated. We're part of a vast, dynamic system, a system that's constantly moving, evolving, changing, and we're all caught in the flow. If you want to see how this cosmic current fits into the larger structure of the universe, watch our next video, where we explore how galaxy clusters and superclusters are all part of this grand cosmic dance toward the Great Attractor. Imagine you're in a small boat floating down a massive river. You feel the current pulling you, but you don't realize you're actually caught in the wake of a giant ship moving ahead of you. That ship is the Virgo cluster, and our local group, including the Milky Way, is like that small boat being swept along in its gravitational wake. The Virgo cluster isn't just another collection of galaxies in space. It's the heavyweight champion of our cosmic neighborhood, and its gravitational pull is so powerful that it's dragging entire clusters of galaxies toward the Great Attractor. Today, we're uncovering how this massive cluster shapes the motion of everything around it, including our own galaxy. Let's start with the basics. The Virgo cluster is a monster, located about 54 million light-years from Earth. It's the closest large cluster of galaxies to us. When I say large, I mean really large. The Virgo contains over 1,300 identified galaxies, though astronomers estimate there might be as many as 2,000 when you count the smaller ones. To put that in perspective, our entire local group has only about 80 galaxies. The Virgo cluster is like a cosmic metropolis compared to our small town. The biggest galaxies in the Virgo cluster are true giants. Messier 87, or M87, is the cluster's dominant galaxy. This elliptical galaxy is about 120,000 light-years across, bigger than our Milky Way, and contains nearly 1 trillion stars. At its center sits a supermassive black hole with the mass of 6.5 billion suns. That's so massive, it makes the black hole at the center of our Milky Way look like a pebble next to a boulder. M87 is famous for that incredible image the Event Horizon Telescope captured in 2019, the first ever photo of a black hole's event horizon. But the Virgo cluster isn't just about M87. It's home to other massive galaxies like Messier 49, Messier 60, and Messier 86. These galaxies, along with hundreds of smaller ones, are all bound together by gravity, creating a cosmic dance that's been going on for billions of years. The cluster spans about 15 million light-years across. That's 150 times the diameter of our Milky Way. If you could see it with the naked eye, it would cover an area of sky as big as 10 full moons side by side. Now, here's where it gets really interesting. The Virgo cluster isn't just sitting there minding its own business. It's moving fast, and it's taking everything around it with it. Astronomers discovered this by measuring the peculiar velocities of galaxies. That's the motion galaxies have beyond the general expansion of the universe. What they found was that the Virgo cluster, along with all its galaxies, is being pulled toward the Great Attractor at about 400 kilometers per second. That's over 1.4 million kilometers per hour. At that speed, you could travel from Earth to the Moon in just 15 minutes. But here's the mind-blowing part. The Virgo cluster's gravitational influence extends far beyond its own galaxies. It's so massive that it affects the motion of everything around it, including our local group. Think of it like this. If the Virgo cluster is a giant ship, then our local group is a small boat caught in its wake. We're not just being pulled directly toward the Great Attractor. We're being pulled toward the Virgo cluster, which is itself being pulled toward the Great Attractor. It's like a cosmic chain reaction. Astronomers call this the Virgo-centric flow. It's the motion of galaxies toward the Virgo cluster due to its gravitational pull. Our local group is falling toward the Virgo cluster at about 200 kilometers per second. That's on top of the general flow toward the Great Attractor. So our total motion through space is a combination of these two flows, like a boat being pulled by two different currents at the same time. The Virgo cluster's gravitational influence extends for hundreds of millions of light-years. It affects not just our local group, but other galaxy groups and clusters in our cosmic neighborhood. The Fornax cluster, the Centaurus A group, the M81 group, they're all being influenced by the Virgo cluster's gravity. Together, these clusters and groups form what astronomers call the Virgo supercluster, and this supercluster is all flowing toward the Great Attractor. But how do astronomers know this? How can they measure something so vast? The answer lies in something called peculiar velocity mapping. Astronomers measure the actual motion of galaxies and compare it to the motion expected from the expansion of the universe. If a galaxy is moving faster than expected, or in a different direction, that means something is pulling it. By mapping these peculiar velocities across the sky, astronomers can create a 3D map of how matter is flowing in the universe. When they did this for our cosmic neighborhood, they found something incredible. Galaxies within about 30 million light-years of the Virgo cluster are all falling toward it. Beyond that, the flow shifts toward the Great Attractor. It's like discovering that rivers in a continent all flow toward a central lake. And beyond that lake, they all flow toward the ocean. The Virgo cluster is that central lake, and the Great Attractor is the ocean. The Virgo cluster's role in this cosmic flow is crucial because it's the most massive structure in our cosmic neighborhood. Its gravity dominates the motion of everything around it. Without the Virgo cluster, the flow of galaxies toward the Great Attractor would be very different. It's like a boulder in a river. It changes the flow of water around it, creating eddies and currents that affect everything downstream. But here's where it gets even more fascinating. The Virgo cluster itself is part of a larger structure called the Laniakea supercluster. Laniakea is Hawaiian for immense heaven, and it's a perfect name for this vast structure. The Laniakea supercluster contains about 100,000 galaxies and spans 500 million light-years. It includes the Virgo cluster, our local group, and hundreds of other galaxy groups and clusters. And the Great Attractor is at the center of it all. The discovery of the Laniakea supercluster in 2014 was a game-changer. Astronomers realized that the flow toward the Great Attractor wasn't just some local curiosity. It was part of the fundamental architecture of the universe. The Virgo cluster, our local group, and everything else in the Laniakea supercluster are all flowing toward the Great Attractor, like water in a cosmic river basin. But what makes the Virgo cluster so special? Why does it have such a powerful gravitational influence? The answer lies in its mass. The Virgo cluster contains an estimated 1.2 quadrillion times the mass of our Sun. That's 1,200,000,000,000,000,000,000 solar masses. About 90% of that mass is dark matter, the mysterious invisible stuff that makes up most of the matter in the universe. This dark matter forms a vast halo around the cluster, extending far beyond the visible galaxies. It's this dark matter halo that creates the powerful gravitational pull affecting everything around it. The Virgo cluster's dark matter halo is so massive that it bends light from objects behind it, a phenomenon called gravitational lensing. Astronomers have used this effect to map the distribution of dark matter in the cluster. What they found was a complex web of dark matter filaments connecting the galaxies within the cluster. These filaments act like cosmic highways, channeling matter toward the center of the cluster. But the Virgo cluster isn't just sitting there pulling everything toward it. It's also evolving. Galaxies within the cluster are colliding and merging. Gas is being stripped from galaxies as they move through the cluster. New stars are forming in some regions, while star formation is being quenched in others. It's a dynamic, ever-changing system that's been evolving for billions of years. One of the most fascinating aspects of the Virgo cluster is its effect on galaxies that fall into it. As galaxies approach the cluster, they experience something called ram pressure stripping. The hot gas within the cluster acts like a cosmic wind, stripping gas from the incoming galaxies. Without gas, these galaxies can't form new stars, so they slowly fade and die. It's like watching a cosmic predator devouring its prey. Our own local group is safe from this fate, for now. We're still far enough from the Virgo cluster that we're not being stripped of our gas, but we're getting closer. In about 100 billion years, the local group will merge with the Virgo cluster. By then, our Milky Way and Andromeda will have already collided to form a single galaxy, which will then merge with the Virgo cluster. It's a cosmic reunion that's been billions of years in the making. The Virgo cluster's connection to the Great Attractor is just one piece of this cosmic puzzle, but it's a crucial piece. It shows how structures on different scales are connected, from individual galaxies to clusters to superclusters. It reveals the hidden architecture of the universe, with vast flows and currents shaped by gravity on the grandest scales. What makes this even more amazing is that we're part of this story. Our Milky Way galaxy, our solar system, our planet, we're all caught in this cosmic flow, swept along by the gravity of the Virgo cluster toward the Great Attractor. We're not just observers of the universe, we're participants in its grand dance. As we continue to map the universe, we're discovering more about these cosmic flows and the structures that shape them. The Virgo cluster is just one piece of a much larger puzzle, a puzzle that includes superclusters, filaments, voids, and the mysterious dark matter and dark energy that make up most of the universe. Each new discovery brings us closer to understanding our place in the cosmos. The Virgo cluster's gravitational role in our cosmic neighborhood is a reminder of how dynamic the universe is. It's not static, it's constantly changing, evolving, moving. Galaxies aren't just sitting there, they're dancing, flowing, being pulled by invisible forces across the cosmos, and we're part of that dance. If you want to see how the Virgo cluster fits into the even larger structure of the Laniakea supercluster, watch our next video where we explore how superclusters are all part of this grand cosmic dance toward the Great Attractor. Imagine you're in a massive crowd where everyone's slowly spreading apart. That's the universe expanding due to the Big Bang. But now, picture some people in that crowd suddenly sprinting sideways or even backward against the flow. That's exactly what galaxies are doing in space. While the universe expands, galaxies aren't just drifting apart uniformly. They're racing, tumbling, and being yanked by invisible forces in directions that defy simple explanation. These wild galactic movements are called peculiar velocities, and they're the cosmic breadcrumbs that led astronomers to discover the Great Attractor. Today, we're unraveling how galaxies break the rules of cosmic expansion and what this reveals about hidden structures in our universe. Let's start with the basics. In the 1920s, Edwin Hubble made a groundbreaking discovery. Almost every galaxy in the universe is moving away from us. The farther away a galaxy is, the faster it's receding. This relationship, now called Hubble's law, became the foundation of our understanding of an expanding universe. It's like dots on an inflating balloon. As the balloon expands, all dots move away from each other, with dots farther apart moving away faster. But here's where things get weird. By the 1970s, astronomers had developed tools precise enough to measure galaxy motions in incredible detail. What they found was that galaxies weren't perfectly following Hubble's law. Some were moving faster away than expected, others slower. Some were even moving toward us instead of away. These deviations from the expected cosmic expansion are what astronomers call peculiar velocities. Think of it like this. If cosmic expansion is a river flowing steadily outward, peculiar velocities are the fish swimming in that river. Some fish swim with the current, moving away faster than expected. Some swim against it, moving toward us, and some dart sideways. These swimming motions are caused by gravitational tugs from massive objects like galaxy clusters and superclusters. The peculiar velocity of our own Milky Way galaxy is a perfect example. Based on Hubble's law, we should be moving away from other galaxies at a predictable speed. But when astronomers measured our actual motion, they found we're rocketing through space at about 600 kilometers per second in a specific direction toward the constellations Centaurus and Hydra. That's over 2 million kilometers per hour, fast enough to circle Earth in just 6 minutes. This motion is so significant, it creates a dipole anisotropy in the cosmic microwave background radiation, the afterglow of the Big Bang. In one direction, the CMB appears slightly hotter, blue-shifted, because we're moving toward it. In the opposite direction, it appears slightly cooler, red-shifted, because we're moving away. But here's the mind-blowing part. Our Milky Way isn't the only galaxy with peculiar velocity. Almost every galaxy has its own swimming motion through space. And when astronomers started mapping these motions across the sky, they discovered something astonishing. Galaxies weren't moving randomly. They were flowing in coordinated patterns, like schools of fish, all swimming in the same direction. And the center of this flow? The Great Attractor. One of the most significant peculiar velocity measurements came from the Seven Samurai, a team of astronomers led by Alan Dressler, Sandra Faber, and others in the 1980s. They studied the motions of about 400 elliptical galaxies and found that our entire local group of galaxies is being pulled toward the Great Attractor region at about 600 kilometers per second. But they also discovered that this flow wasn't uniform. Galaxies closer to the Great Attractor were moving faster than those farther away, exactly as you'd expect if they were being pulled by a massive gravitational source. The technique they used was brilliant. Astronomers measure a galaxy's peculiar velocity by comparing its actual motion with the motion expected from cosmic expansion. Here's how it works. First, they measure the galaxy's redshift to determine how fast it's moving away from us due to cosmic expansion. Then, they use other methods to determine the galaxy's actual distance. If the galaxy is closer or farther than expected, based on its redshift, that difference reveals its peculiar velocity. For example, If a galaxy appears to be 100 million light-years away, based on its redshift, but other distance measurements show it's actually only 90 million light-years away, that means it's moving toward us faster than cosmic expansion would predict. The difference between these measurements gives astronomers the galaxy's peculiar velocity, but measuring distances to galaxies is incredibly tricky. Astronomers use something called the cosmic distance ladder, a series of overlapping techniques that build on each other. For nearby galaxies, they use Cepheid variable stars, pulsating stars whose brightness is related to their pulse rate. For farther galaxies, they use Type 1a supernovae, exploding stars with consistent brightness. For the most distant galaxies, they use the Tully-Fisher relation, a correlation between a spiral galaxy's rotational speed and its brightness. Each step on this ladder has its own uncertainties, and these errors accumulate when measuring peculiar velocities. That's why early measurements of the Great Attractor were so controversial. Some astronomers argued that the peculiar velocities might be measurement errors rather than evidence of a massive gravitational source. But as technology improved and measurements became more precise, the evidence became undeniable. One of the most compelling pieces of evidence came from studying the Virgo cluster, which we discussed in the previous chapter. The Virgo cluster is so massive that it creates its own peculiar velocity field. Galaxies within about 30 million light-years of the cluster are all falling toward it at speeds up to 200 kilometers per second. This Virgo-centric flow is superimposed on the larger flow toward the Great Attractor. By carefully mapping these velocities, astronomers could separate the local influence of the Virgo cluster from the larger influence of the Great Attractor. But peculiar velocities aren't just about the Great Attractor. They reveal a complex gravitational landscape across the entire universe. One of the most surprising discoveries was the dipole repeller, a region of space that seems to be pushing galaxies away rather than pulling them in. Located in the opposite direction from the Great Attractor, the dipole repeller is a vast void with relatively little matter. Galaxies near this void are being pushed away by the lack of gravitational pull, creating a repulsive effect that works in tandem with the attractive pull of the Great Attractor. Think of it like a cosmic seesaw. The Great Attractor is the heavy end pulling galaxies toward it, while the dipole repeller is the light end pushing galaxies away. Our Milky Way and the local group are caught in the middle, being pulled by the Great Attractor and pushed by the dipole repeller. This combination of attraction and repulsion creates the peculiar velocity we observe. Another fascinating example of peculiar velocities is the Bullet Cluster, two galaxy clusters that collided billions of years ago. During the collision, the hot gas in the clusters slowed down due to friction, but the dark matter, which doesn't interact with gas, kept moving at high speed. This created a situation where the galaxies and dark matter are separated from the hot gas, moving with their own peculiar velocities. The Bullet Cluster became famous because it provided direct evidence for dark matter, the mysterious invisible stuff that makes up about 27% of the universe. Peculiar velocities also reveal the existence of vast cosmic structures beyond what we can see. For example, the Shapley supercluster, a massive concentration of galaxy clusters located about 650 million light-years away, has such a strong gravitational pull that it affects the peculiar velocities of galaxies hundreds of millions of light-years away. The Shapley supercluster is so massive that it's actually pulling the Great Attractor toward it, creating a hierarchy of gravitational influences that extends across the observable universe. But measuring peculiar velocities isn't just about mapping cosmic structures. It's also about understanding the fundamental properties of the universe. By studying how galaxies move, astronomers can test theories of gravity, measure the amount of dark matter, and even probe the nature of dark energy, the mysterious force causing the expansion of the universe to accelerate. One of the most ambitious projects in this field is the Cosmic Flows program, led by astronomer Brent Tully. His team has mapped the peculiar velocities of over 18,000 galaxies to create a 3D map of how matter is flowing in the nearby universe. What they found was a complex network of flows, with galaxies moving like water in a vast cosmic river system. These flows reveal the underlying gravitational landscape, the hills and valleys of gravity created by the distribution of matter in the universe. The cosmic flows maps show that our local group is part of a larger flow toward the great attractor, which itself is part of an even larger flow toward the Shapley supercluster. It's like discovering that your local river is part of a larger watershed, which is part of an even larger continental drainage system. Each level reveals a larger structure pulling on the one before it. But perhaps the most mind-blowing aspect of peculiar velocities is what they tell us about our place in the universe. We're not just floating in empty space. We're on a journey that began billions of years ago and will continue for billions more. Our Milky Way galaxy is being pulled toward the great attractor at breakneck speed, while the great attractor itself is being pulled toward the Shapley supercluster. We're part of a cosmic dance that's been going on since the beginning of time. And here's the craziest part. We're moving through space so fast that if you could see the universe from outside, you'd see our entire local group, the Milky Way, Andromeda, Triangulum, and all the smaller galaxies, streaking through the cosmos like a cosmic bullet. We're all in this together, caught in the same gravitational current, swept along by invisible forces toward a destination we'll never reach in our lifetime. The study of peculiar velocities has transformed our understanding of the universe. It's revealed that the cosmos isn't just expanding uniformly. It's got this complex internal structure with vast flows and currents shaped by gravity on the grandest scales. These flows are the cosmic fingerprints of dark matter and dark energy, the mysterious components that make up 95% of the universe. As we continue to map peculiar velocities with ever greater precision, we're uncovering new details about the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. Each new measurement brings us closer to understanding the hidden architecture of the cosmos and our place within it. The peculiar velocities of galaxies are more than just interesting scientific data. They're the story of our cosmic journey, a journey that began with the Big Bang and will continue until the end of time. We're all part of this journey, swept along by invisible forces toward a cosmic destiny we're only beginning to understand. If you want to see how these peculiar velocities fit into the larger cosmic web and reveal the hidden structure of the universe, watch our next video, where we explore the cosmic web and how it shapes the motion of galaxies across the universe. Imagine trying to map an entire city using only a flashlight. You'd see the streetlights, the cars, the people walking by, but you'd miss the buildings, the roads, the entire infrastructure holding it all together. That's exactly what astronomers faced when trying to understand the great attractor. They could see galaxies moving, but the cause of that motion, the hidden mass pulling everything, remained invisible. How do you map something you can't see? Today, we're uncovering the brilliant tools and techniques astronomers developed to track this invisible cosmic architecture, revealing the hidden hand shaping our universe. The biggest problem was simple. The great attractor region was hiding behind the Milky Way's thick dust clouds, and even where it was visible, the force pulling galaxies seemed way too powerful for the visible matter astronomers could detect. They knew something massive was there, but what? The answer lay in developing clever ways to detect matter that doesn't shine, doesn't reflect light, and doesn't interact with anything electromagnetically. In other words, dark matter and the complex structures it forms. Let's start with one of the most powerful tools in the cosmic detective kit: gravitational lensing. This is like nature's own magnifying glass. Einstein's theory of general relativity told us that massive objects bend the fabric of space-time itself. When light from a distant galaxy passes near a massive object, like a galaxy cluster, on its way to us, that gravity bends the light's path. It can distort the galaxy's image, stretch it, or even create multiple images of the same galaxy. By carefully studying these distortions, astronomers can map exactly where the mass is, even if that mass is completely dark. Think of it like looking at a distorted reflection in a funhouse mirror. You might not see the mirror itself clearly, but you can figure out its shape by how it warps your reflection. That's exactly what astronomers do with gravitational lensing. They look at how distant galaxies appear warped or duplicated, and from that, they calculate the mass distribution of the cluster causing the warping. This technique became crucial for studying the Great Attractor region, because it didn't rely on seeing light from the hidden mass, only seeing how it affected light passing by it. One of the most famous examples is the Bullet Cluster, two galaxy clusters that collided billions of years ago. When astronomers mapped the mass using gravitational lensing, they found something astonishing. Most of the mass wasn't where the visible galaxies and hot gas were. It was in separate clumps, offset from the visible matter. This was direct, visual proof that dark matter exists and behaves differently from normal matter. This same technique, applied to the Great Attractor region, revealed vast clouds of dark matter, far more massive than any visible structures could account for. But gravitational lensing has its limits. It works best for very distant objects lined up perfectly behind massive clusters. For mapping the broader structure around the Great Attractor, astronomers needed another tool: X-ray astronomy. Galaxy clusters aren't just collections of galaxies. They're filled with incredibly hot gas, heated to millions of degrees by the immense gravity of the cluster. This superheated gas glows brightly in X-rays, invisible to our eyes but detectable by special telescopes in space. Telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton became cosmic smoke detectors, spotting the faint X-ray glow from this hot gas. By mapping where this gas was and how hot it was, astronomers could calculate the total mass needed to hold it in place. If the gas is 10 million degrees and spread across millions of light years, you need an enormous amount of gravity to keep it from flying apart. This gravity comes from the total mass of the cluster, both visible stars and galaxies, and the invisible dark matter. When X-ray telescopes pointed toward the Great Attractor region, they found several massive galaxy clusters glowing brightly in X-rays, like the Norma cluster, ACO 3627. These clusters were big, but again, when astronomers added up all the mass they could account for, the galaxies, the hot gas, everything visible, it still wasn't enough to explain the gravitational pull affecting our Milky Way. The X-ray maps confirmed what gravitational lensing suggested. There had to be much more mass there than we could see, hidden in the form of dark matter. Another crucial tool came from radio astronomy. Remember the zone of avoidance? That thick band of dust in our galaxy blocking visible light? Well, radio waves pass right through dust like it's not even there. Radio telescopes, like the Very Large Array in New Mexico or the Parkes Observatory in Australia, became cosmic penetrating radar, seeing through the Milky Way's dust to map what lay beyond. Astronomers used radio telescopes to detect something called the 21 centimeter line. This is a specific radio wavelength emitted by neutral hydrogen gas, the raw material galaxies use to form stars. By mapping this hydrogen gas, astronomers could trace where galaxies were, even if they were hidden behind dust. They found entire galaxy clusters and filaments of gas in the zone of avoidance, structures completely invisible to optical telescopes. This helped fill in the gaps in the map around the Great Attractor, revealing a complex network of matter flowing toward it. But perhaps the most revolutionary tool for mapping the Great Attractor came from redshift surveys. These surveys measure how fast galaxies are moving away from us by looking at how much their light has been stretched or redshifted by the expansion of the universe. By measuring redshifts for thousands of galaxies, astronomers can create 3D maps of how matter is distributed in space. One of the most important of these was the 2MASS Redshift Survey, 2MRS. Using infrared telescopes that could see through dust better than optical telescopes, 2MRS mapped the positions and distances of over 43,000 galaxies across the entire sky, including the previously hidden zone of avoidance. What they found was a complex web of galaxies, clusters, and superclusters, all interconnected by filaments of matter. The Great Attractor appeared as a massive concentration at the center of this web, with galaxies flowing toward it from all directions. Building on this, the Cosmic Flows 3 survey, led by astronomer Brent Tully, took things even further. His team measured the distances and motions of over 18,000 galaxies to create the most detailed 3D map ever made of our cosmic neighborhood. They used multiple distance measurement techniques, from Cepheid variable stars for nearby galaxies to the Tully-Fisher relation, which links a spiral galaxy's rotation speed to its brightness for more distant ones. By comparing these distances with redshifts, they could calculate each galaxy's peculiar velocity, its motion beyond the simple expansion of the universe. The Cosmic Flows 3 map was stunning. It revealed vast rivers of galaxies flowing toward the Great Attractor, like water in a cosmic watershed. Our local group, the Virgo cluster, the Hydra Centaurus supercluster, all were part of this flow, being pulled toward the Great Attractor at hundreds of kilometers per second. But the map also showed something else. The Great Attractor itself was moving, flowing towards something even larger. The Shapley supercluster, located about 650 million light-years away. It was like discovering that your local river is part of a larger river system flowing toward the ocean. But how do astronomers make sense of all this data? How do they connect the dots between gravitational lensing maps, X-ray observations, radio surveys, and redshift measurements? The answer lies in computer simulations. Modern supercomputers can simulate the evolution of the entire universe, starting from the tiny fluctuations in density just after the Big Bang and running forward for 13.8 billion years. These simulations model how dark matter collapses under gravity to form the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. They show how galaxies form at the intersections of these filaments, and how clusters grow by merging with other clusters. By comparing these simulations with real observations, astronomers can test their understanding of dark matter, dark energy, and the fundamental laws of physics. One of the most important simulations is the Millennium simulation, which modeled the evolution of over 10 billion particles of dark matter in a cube of space over 2 billion light-years across. The results were breathtaking. The simulation produced a cosmic web strikingly similar to what astronomers observe in the real universe, with vast voids, long filaments, and massive clusters at the nodes where filaments intersect. When astronomers compared this with the Cosmic Flows 3 map, they found that the Great Attractor region matched perfectly with a massive node in the simulated cosmic web, a point where multiple dark matter filaments converged. But simulations do more than just confirm observations. They help astronomers interpret what they see. For example, simulations showed that the peculiar velocities of galaxies, their motion beyond cosmic expansion, are caused by the gravity of the underlying dark matter distribution. By running simulations with different amounts of dark matter or different types of dark energy, astronomers can see which models best match the observed motions of galaxies. This helps them understand not just the Great Attractor, but the fundamental properties of the universe itself. Another powerful tool for mapping invisible mass comes from studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang. This radiation is incredibly uniform across the sky, but it has tiny temperature fluctuations, regions slightly hotter or colder than average. These fluctuations correspond to density variations in the early universe, just 380,000 years after the Big Bang. By mapping these fluctuations with satellites like WMAP and Planck, astronomers can create a picture of the universe's initial conditions. They can then run simulations forward to see how these tiny fluctuations grew into the large-scale structures we see today, including the Great Attractor. The Planck satellite's map of the CMB was so precise that it allowed astronomers to measure the exact amounts of dark matter and dark energy in the universe, confirming that dark matter makes up about 27% of the universe, while dark energy makes up about 68%. But how does this help map the Great Attractor specifically? The CMB also shows something called the Sunyaev-Zeldovich effect. When CMB radiation passes through a hot galaxy cluster, the high-energy electrons in the cluster's gas can give some of their energy to the CMB photons, creating a tiny distortion in the CMB map. By mapping these distortions, astronomers can detect galaxy clusters even if they're hidden behind dust or too distant to see directly. This technique has helped astronomers find previously unknown clusters in the Great Attractor region. One of the most exciting new tools for mapping invisible mass is weak gravitational lensing. Unlike strong lensing, which creates dramatic distortions like multiple images or Einstein rings, weak lensing creates subtle distortions in the shapes of distant galaxies. By statistically analyzing the shapes of thousands of galaxies, astronomers can map the distribution of dark matter across huge areas of the sky. The Dark Energy Survey, DES, used this technique to map dark matter in an eighth of the sky. They found vast cosmic web structures, with dark matter concentrated in filaments and clusters. When they overlaid their dark matter map with maps of visible galaxies, they found that the galaxies followed the dark matter distribution perfectly, like leaves floating on the surface of a deep river, tracing the currents below. This confirmed that dark matter forms the scaffolding upon which the visible universe is built. All these tools, gravitational lensing, X-ray observations, radio astronomy, redshift surveys, computer simulations, CMB mapping, and weak lensing, work together to create a comprehensive picture of the invisible universe. Each technique provides a different piece of the puzzle, and when combined, they reveal the hidden architecture shaping the motion of galaxies. For the Great Attractor specifically, this multi-pronged approach revealed something astonishing. The Great Attractor isn't a single object, or even a single cluster. It's a vast region of space, where multiple dark matter filaments converge, creating a gravitational well so deep that it pulls in galaxies from hundreds of millions of light-years around. The visible galaxy clusters in the region, like the Norma cluster, are just the tip of the iceberg, the visible peaks of a massive dark matter mountain range beneath. The mapping also showed that the Great Attractor is part of an even larger structure called the Laniakea supercluster. Laniakea, which means immense heaven in Hawaiian, contains about 100,000 galaxies and spans 500 million light-years. The Great Attractor sits near its center, acting as the gravitational focal point for the entire supercluster. Our Milky Way, along with everything else in Laniakea, is flowing toward this focal point, like water down a drain. But perhaps the most profound realization from all this mapping is that the Great Attractor isn't unique. The universe is filled with similar structures, vast concentrations of mass that shape the motion of galaxies across cosmic distances. The Shapley supercluster, the Perseus-Pisces supercluster, the Coma supercluster, each is a massive node in the cosmic web, pulling galaxies toward it in a grand cosmic dance. What makes the Great Attractor special is its proximity and its effect on our own galaxy. We're not just observers of this cosmic phenomenon, we're participants. Our Milky Way is being pulled toward the Great Attractor at over 600 kilometers per second, caught in the same gravitational current as thousands of other galaxies. We're part of this vast, invisible structure flowing through space toward a destination we'll never reach in our lifetime. The tools astronomers developed to map these invisible influences are more than just scientific instruments. They're windows into the hidden architecture of the universe, revealing the dark matter and dark energy that make up 95% of everything. They show us that the universe isn't empty space dotted with galaxies. It's a complex, dynamic web of matter and energy, shaped by gravity on the grandest scales. As technology continues to advance, these tools will become even more powerful. New telescopes, like the James Webb Space Telescope, are peering deeper into the zone of avoidance than ever before, using infrared vision to see through dust and reveal the hidden structures behind it. New radio telescopes, like the Square Kilometre Array, will map the distribution of hydrogen gas with unprecedented precision, tracing the cosmic web in 3 dimensions. And new computer simulations will model the universe with ever greater detail, helping us understand how the Great Attractor and similar structures formed and evolved. Each new discovery brings us closer to solving the mystery of the Great Attractor, but more importantly, each discovery reveals something new about the universe itself, its structure, its history, and its ultimate fate. The Great Attractor isn't just a curiosity. It's a key to understanding the fundamental forces that shape our cosmos. If you want to see how all these invisible structures connect to form the cosmic web, the vast network that shapes the entire universe, watch our next video, where we explore the largest structures in existence and how they reveal the hidden architecture of everything. Imagine standing in a forest at night. You can't see the entire forest, but you can hear the wind moving through the trees. By listening carefully to how the wind rustles different branches, you can start to map the shape of the forest around you, where the dense thickets are, where the clearings lie. That's exactly what astronomers do when they study the motion of galaxies. Each galaxy is like a tree in the cosmic forest, and its motion through space reveals the invisible structures shaping the universe around it. Today, we're uncovering how these galactic movements weave together to reveal the grand tapestry of the cosmos. A tapestry so vast, it stretches across billions of light years. Let's start with something mind-blowing. When astronomers mapped the peculiar velocities of thousands of galaxies, they didn't just find random motions, they found patterns, coordinated flows, vast rivers of galaxies all moving in the same direction. It was like discovering that all the rivers in a continent flow toward the same ocean. These flows weren't random. They were tracing the underlying structure of the universe itself. And what they revealed was a cosmic web so vast, it defies imagination. The first clue came from the Sloan Digital Sky Survey, SDSS, one of the most ambitious astronomical projects ever undertaken. Over 14 years, SDSS mapped the positions and distances of over 3 million galaxies. When astronomers plotted these galaxies in 3D, they saw something astonishing. Galaxies weren't scattered randomly through space. They were arranged in a vast, intricate web. Long filaments of galaxies stretched across hundreds of millions of light years, connecting massive nodes where thousands of galaxies clustered together. Between these filaments were enormous voids, regions of space almost completely empty of galaxies, some spanning hundreds of millions of light years. This cosmic web wasn't just a pretty picture. It was the skeleton of the universe, and the motion of galaxies was the blood flowing through its veins. Galaxies weren't just sitting on this web. They were moving along it, flowing from the voids into the filaments, and from the filaments into the clusters. It was like watching water flow through a network of streams and rivers, all eventually draining into massive lakes. But here's where it gets really interesting. The motion of galaxies wasn't just tracing the visible structure. It was revealing something invisible, the dark matter that makes up most of the universe. Dark matter doesn't emit light, so we can't see it directly, but it has gravity, and that gravity affects the motion of galaxies. By studying how galaxies move, astronomers could map where the dark matter was. Think of it like this. If you see leaves floating down a river, you can infer the shape of the riverbed beneath the surface, even if you can't see it. The leaves follow the currents created by the underwater landscape. In the same way, galaxies follow the gravitational currents created by the underlying dark matter distribution. One of the most important discoveries came from the 2 MASS redshift survey, which we mentioned earlier. This survey mapped over 43,000 galaxies across the entire sky, including the previously hidden zone of avoidance. What they found was that our local group of galaxies, including the Milky Way, wasn't just moving randomly through space. We were part of a vast flow of galaxies, all moving toward the same region, the Great Attractor. But the Great Attractor wasn't the end of the story. As astronomers mapped more galaxies, they realized that the flow toward the Great Attractor was itself part of an even larger flow. Galaxies weren't just moving toward the Great Attractor, they were moving through it, continuing toward something even farther away. It was like discovering that the river you're following doesn't end at the lake you thought was its destination. It flows out of the lake and continues toward the ocean. This led to the discovery of the Laniakea supercluster in 2014. Laniakea means immense heaven in Hawaiian, and it's a perfect name for this vast structure. Laniakea contains about 100,000 galaxies and spans 500 million light-years. It includes our local group, the Virgo cluster, the Great Attractor, and hundreds of other galaxy groups and clusters. And all of these galaxies are flowing toward a single point, the Great Attractor. But how did astronomers discover Laniakea? They used a clever technique based on peculiar velocities. By measuring how galaxies are moving beyond the simple expansion of the universe, they could map the gravitational landscape. Galaxies within a certain region are all flowing toward the same gravitational center. That region is Laniakea. Beyond its boundaries, galaxies are flowing toward other gravitational centers, like the Perseus-Pisces supercluster. The discovery of Laniakea was revolutionary. It showed that superclusters aren't just collections of galaxies. They're coherent structures with defined boundaries, like watersheds on Earth. Just as all the rivers in a watershed flow toward the same ocean, all the galaxies in Laniakea flow toward the Great Attractor. This gave astronomers a whole new way to map the large-scale structure of the universe. But Laniakea itself is part of something even larger. The flow toward the Great Attractor is being influenced by an even more massive structure, the Shapley supercluster. Located about 650 million light-years away, the Shapley supercluster is one of the largest known structures in the universe. It contains thousands of galaxy clusters and has a mass equivalent to more than 10,000 Milky Way galaxies. Its gravitational pull is so strong that it's affecting the motion of the entire Laniakea supercluster, including our own Milky Way. Think of it like a hierarchy of gravitational influences. The Shapley supercluster is pulling on Laniakea, which is pulling on the Great Attractor, which is pulling on the Virgo cluster, which is pulling on our local group. It's like a set of nested Russian dolls, with each level influencing the one inside it. Our Milky Way is caught in this complex gravitational cascade, being pulled by forces on scales almost too large to comprehend. But what creates this cosmic web? Why is the universe structured this way? The answer lies in the early universe. Just after the Big Bang, the universe was incredibly uniform, with tiny fluctuations in density, regions slightly denser or less dense than average. Over billions of years, gravity amplified these differences. The denser regions pulled in more matter, becoming even denser, while the less dense regions became emptier. This process created the cosmic web we see today. The densest regions became galaxy clusters and superclusters, connected by filaments of dark matter and galaxies. The emptiest regions became the vast voids, and the motion of galaxies traces this structure, flowing from the voids into the filaments, and from the filaments into the clusters. One of the most powerful tools for understanding this process is computer simulation. Supercomputers can simulate the evolution of the universe from these tiny fluctuations after the Big Bang to the complex cosmic web we see today. The Millennium simulation, which we mentioned earlier, modeled over 10 billion particles of dark matter evolving over billions of years. The results were stunning, a cosmic web strikingly similar to what astronomers observe in the real universe. These simulations show how dark matter collapses under gravity to form filaments and nodes. Galaxies form at the intersections of these filaments, where the density is highest. The simulations also show how galaxies move along these filaments, flowing toward the densest regions. It's like watching the cosmic web come alive, with galaxies as tracers revealing the invisible dark matter structure beneath. But simulations do more than just reproduce what we see. They help us understand why the universe looks this way. By running simulations with different amounts of dark matter or different types of dark energy, astronomers can test their theories about the fundamental properties of the universe. The fact that simulations with the observed amounts of dark matter and dark energy produce a cosmic web matching our observations is strong evidence that our understanding is correct. Another crucial piece of evidence comes from the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB shows tiny temperature fluctuations that correspond to density variations in the early universe. By mapping these fluctuations with satellites like Planck, astronomers can see the seeds of the cosmic web, the tiny ripples that grew into the vast structures we see today. What's remarkable is that the patterns in the CMB match the patterns we see in the distribution of galaxies today. The regions that were slightly denser in the early universe became the galaxy clusters and superclusters we see now. The regions that were slightly less dense became the voids. The motion of galaxies today is tracing the gravitational influence of these primordial density fluctuations, amplified by billions of years of cosmic evolution. But perhaps the most profound insight from studying galaxy motions is that the universe isn't static, it's dynamic, evolving, flowing. Galaxies aren't just sitting in space, they're on journeys that last billions of years. Our Milky Way is on such a journey, being pulled toward the Great Attractor at over 600 kilometers per second, and the Great Attractor itself is being pulled toward the Shapley supercluster. We're all part of this cosmic flow, caught in currents that have been flowing since the beginning of time. This perspective changes how we see our place in the universe. We're not just floating in empty space. We're part of a vast, dynamic structure, a cosmic tapestry woven from the threads of gravity, dark matter, and galaxy motions. We're on a journey that began billions of years ago and will continue for billions more. The study of galaxy motions has revealed that the universe is more interconnected than we ever imagined. Galaxies, hundreds of millions of light years apart, are influencing each other's motion through gravity. Structures like the Great Attractor and the Shapley supercluster are shaping the flow of galaxies across vast cosmic distances. We're all part of this grand cosmic dance, moving to the rhythm of gravity on the largest scales. As we continue to map the universe with ever greater precision, we're discovering more details about this cosmic tapestry. New telescopes like the James Webb Space Telescope are peering deeper into the zone of avoidance, revealing previously hidden structures. New surveys, like the Dark Energy Survey, are mapping the distribution of dark matter with unprecedented detail, and new computer simulations are modeling the universe with ever greater complexity, helping us understand how the cosmic web formed and evolved. Each new discovery adds another thread to the tapestry, revealing more of the hidden architecture of the universe. The Great Attractor, once a mysterious anomaly, is now understood as a crucial part of this architecture, a node in the cosmic web where multiple filaments converge, creating a gravitational well that influences the motion of galaxies across hundreds of millions of light years. But perhaps the most amazing thing about all this is that we can understand it at all. We're tiny beings on a small planet, orbiting an average star in an ordinary galaxy, yet we've managed to map the structure of the observable universe and understand the forces that shape it. We've discovered that we're part of something vast and beautiful, a cosmic tapestry woven from the threads of gravity, dark matter, and galaxy motions, stretching across billions of light years and billions of years. The motion of galaxies is more than just interesting scientific data. It's the story of our cosmic journey, a journey that began with the Big Bang and will continue until the end of time. We're all part of this journey, swept along by invisible forces toward a cosmic destiny we're only beginning to understand. If you want to see how this cosmic tapestry connects to the largest structures in the universe and what it reveals about our cosmic destiny, watch our next video, where we explore the ultimate fate of the Great Attractor and everything being pulled toward it. Imagine you're trying to see a mountain range right in front of you, but there's a thick fog blocking your view. You know something massive is out there. You can feel its gravity pulling you. You can see its effects on everything around it, but you just can't see it. That's exactly the problem astronomers faced with the Great Attractor. For decades, the most mysterious gravitational force in our cosmic neighborhood hid behind the Milky Way's thick curtain of interstellar dust. But then came a revolution in astronomy. New eyes that could see through the cosmic fog. Today, we're uncovering how infrared light became our superpower, finally revealing what lurks in the zone of avoidance and changing our understanding of the Great Attractor forever. Let's start with the problem. Our Milky Way galaxy is beautiful, but it's also messy. It's filled with giant clouds of gas and dust, the raw material for new stars and planets. These dust clouds are like cosmic smoke. They don't emit light, and they absorb or scatter the visible light from objects behind them. The thickest band of this dust runs along the plane of our galaxy, creating what astronomers call the zone of avoidance, a region covering about 20% of the entire night sky where our view is completely blocked. And guess what? The Great Attractor sits right smack in the middle of this cosmic blind spot. It's like the universe played a cruel joke on us, hiding one of its biggest mysteries behind our own galactic backyard. For years, astronomers could only study the Great Attractor indirectly, by measuring how it affected the motion of galaxies around it. They knew something massive was there, but they couldn't see it directly. It was like trying to study an elephant by only looking at its footprints in the sand. But then came a breakthrough. Scientists realized that while the dust blocks visible light, it doesn't block all types of radiation. Different wavelengths of light behave differently when they hit dust clouds. Some can pass right through, while others get absorbed. And one type of light that's particularly good at penetrating dust is infrared. Infrared light is just light with longer wavelengths than what our eyes can see. It's the same kind of light that heat lamps use, or that thermal cameras detect. Anything with a temperature above absolute zero emits infrared radiation. Stars, planets, galaxies, they all glow in infrared, even if they're hidden behind dust. The first astronomers to realize this potential were pioneers like Frank Lowe and Jerry Neugebauer in the 1960s. They developed some of the first infrared telescopes, essentially attaching infrared detectors to existing optical telescopes. What they saw was astonishing. Regions of space that appeared dark and empty in visible light were glowing brightly in infrared. They were seeing through the cosmic fog for the first time. But these early infrared observations were limited. Earth's atmosphere absorbs most infrared radiation, so ground-based telescopes could only see through narrow atmospheric windows. To really unlock the potential of infrared astronomy, astronomers needed to get above the atmosphere, and that's exactly what they did. The first major infrared space telescope was the Infrared Astronomical Satellite, IRAS, launched in 1983. For 10 months, IRAS scanned the entire sky in infrared light, creating the first all-sky infrared map. What it revealed was revolutionary. Behind the Milky Way's dust, IRAS found entire galaxies and galaxy clusters that had been completely invisible before. It was like putting on night vision goggles in a dark room and suddenly seeing a whole new world. IRAS was particularly important for studying the Great Attractor region. It mapped the distribution of infrared-emitting galaxies behind the zone of avoidance. revealing that there was indeed a concentration of mass in that direction. But IRAS had its limitations. Its resolution was relatively low, so it couldn't see fine details, and it couldn't measure distances to these galaxies very accurately. Astronomers knew there was something there, but they still couldn't see it clearly. The next big leap came with the Spitzer Space Telescope, launched in 2003. Spitzer was far more sensitive than IRAS, with much better resolution. It could see fainter objects and distinguish finer details, and it had a special trick. It could observe in the mid-infrared range, which is particularly good at penetrating the thickest dust clouds. Spitzer transformed our view of the zone of avoidance. It revealed galaxy clusters, star-forming regions, and even individual stars behind the Milky Way's dust. For the Great Attractor specifically, Spitzer mapped the distribution of galaxies in unprecedented detail. What it found was a complex network of galaxy clusters and superclusters, all interconnected by filaments of dark matter. The Great Attractor wasn't a single object. It was a vast region where multiple cosmic structures converged. But Spitzer's most important contribution was measuring the distances to these hidden galaxies. By using a special technique called the infrared Tully-Fisher relation, astronomers could determine how far away these galaxies were based on their infrared brightness and rotational speed. This allowed them to create a 3D map of the Great Attractor region for the first time. What they found was that the mass concentration was even larger and more complex than they had imagined. Then came the Wide Field Infrared Survey Explorer, WISE. Launched in 2009, WISE was designed to scan the entire sky in infrared light with even greater sensitivity than Spitzer. Over its mission, WISE detected hundreds of millions of objects, including asteroids, stars, and galaxies. For the Great Attractor, WISE provided the most complete infrared map ever made of the zone of avoidance. What made WISE particularly powerful was its ability to detect the most luminous infrared galaxies that are forming stars at a furious rate. These galaxies are often hidden behind dust, but they glow brightly in infrared. By mapping these galaxies, WISE revealed the underlying structure of the Great Attractor region. It showed vast filaments of galaxies flowing toward the gravitational center, confirming that the Great Attractor was indeed the focal point of a massive cosmic watershed. But perhaps the most revolutionary infrared telescope is the James Webb Space Telescope, JWST, launched in 2021. JWST is the most powerful space telescope ever built, with a mirror 6.5 meters across and instruments designed to observe primarily in infrared. Its sensitivity and resolution are unprecedented, allowing it to see objects that are faint, distant, or hidden behind dust. JWST has already transformed our understanding of the early universe, but it's also proving invaluable for studying the Great Attractor. Its powerful infrared vision can peer through the thickest dust clouds in the zone of avoidance, revealing galaxies and structures that were previously invisible. Early observations from JWST are showing that the Great Attractor region is even more complex than we thought, with multiple layers of structure and interactions that we're only beginning to unravel. But how does infrared light actually penetrate dust? It all comes down to the size of the dust particles compared to the wavelength of light. The dust grains in interstellar space are tiny, typically less than a micron across. Visible light has wavelengths between 400 and 700 nanometers, which is similar in size to the dust grains. When visible light hits these dust grains, it gets scattered or absorbed, like a car trying to drive through a forest of trees. Infrared light, on the other hand, has much longer wavelengths, from about 1 micron to 100 microns. These longer wavelengths can pass right between the dust grains without being scattered, like a person walking through the same forest without hitting any trees. That's why infrared telescopes can see through dust that blocks visible light. This property makes infrared astronomy particularly powerful for studying regions like the Great Attractor, where dust obscures our view. But infrared light also reveals different aspects of the universe than visible light. For example, it's particularly good at detecting cold objects, things like protostars forming inside dust clouds, or planets orbiting distant stars. It's also excellent for studying redshifted light from distant galaxies. As galaxies move away from us, due to the expansion of the universe, their light gets stretched toward longer wavelengths. For very distant galaxies, this can shift visible light into the infrared range. For the Great Attractor specifically, infrared astronomy has been transformative. It has allowed astronomers to map the distribution of galaxies behind the zone of avoidance, measure distances to these galaxies to create 3D maps, identify galaxy clusters and superclusters hidden by dust, trace the flow of galaxies toward the gravitational center, estimate the total mass of the Great Attractor region. What they've found is that the Great Attractor isn't a single object or even a single cluster. It's a vast region of space where multiple dark matter filaments converge, creating a gravitational well so deep that it pulls in galaxies from hundreds of millions of light years around. The visible galaxy clusters in the region, like the Norma cluster, are just the tip of the iceberg, the visible peaks of a massive dark matter mountain range beneath. Infrared observations have also revealed that the Great Attractor is part of an even larger structure called the Laniakea supercluster. Laniakea contains about 100,000 galaxies and spans 500 million light-years. The Great Attractor sits near its center, acting as the gravitational focal point for the entire supercluster. Our Milky Way, along with everything else in Laniakea, is flowing toward this focal point, like water down a drain. But infrared astronomy isn't just about seeing through dust. It's also about seeing the universe in a different light. Literally, infrared reveals processes and structures that are invisible in other wavelengths. For example, it can show us where stars are forming inside dark clouds, or where black holes are hidden behind thick veils of gas and dust. It's like having a new sense that allows us to perceive aspects of the universe that were previously hidden. The development of infrared astronomy is a perfect example of how technological innovation drives scientific discovery. Each new telescope, from IRAS to Spitzer to WISE to JWST, has built on the capabilities of the previous one, revealing more detail and deeper insights. It's a story of human ingenuity and curiosity, of finding new ways to explore the universe and solve its mysteries. And the story isn't over yet. Future infrared telescopes, like the proposed Origins Space Telescope, will be even more powerful, with the ability to map the entire sky in infrared with unprecedented sensitivity and resolution. These telescopes will allow us to study the Great Attractor and other cosmic structures in even greater detail, revealing new insights into the formation and evolution of the universe. What makes this all so remarkable is that we're using technology to overcome a limitation imposed by our position in the universe. We're inside the Milky Way, and our galaxy's dust blocks our view of a significant portion of the cosmos. But instead of accepting this limitation, we've developed new tools, new eyes to see through the dust. We've turned a disadvantage into an opportunity for discovery. The story of infrared astronomy and the Great Attractor is also a story of persistence. Astronomers knew something massive was hidden behind the zone of avoidance, but they couldn't see it. Instead of giving up, they kept developing new techniques and new technologies, pushing the boundaries of what's possible. Decades of effort and innovation have finally allowed us to see through the cosmic veil and reveal the hidden architecture of the universe. And what we've found is more amazing than we could have imagined. The Great Attractor isn't just some local curiosity. It's a crucial part of the cosmic web, the vast network of filaments and voids that make up the large-scale structure of the universe. It's a gravitational focal point where multiple cosmic flows converge, shaping the motion of galaxies across hundreds of millions of light years. Infrared astronomy has given us a new perspective on our place in the universe. We're not just floating in empty space, we're part of a vast, dynamic structure, a cosmic tapestry woven from the threads of gravity, dark matter, and galaxy motions. And thanks to our infrared eyes, we're finally beginning to see this tapestry in all its glory. If you want to discover how radio astronomy is providing even more details about the Great Attractor and revealing structures that even infrared can't see, watch our next video where we explore how radio waves are piercing the cosmic veil in a whole new way. Imagine standing on a beach at night, feeling a powerful current pulling at your legs. You can't see what's causing it. No waves, no wind, but you feel its force tugging you out to sea. That's exactly what astronomers experienced when they first detected the Norma cluster. Hidden behind the Milky Way's thick curtain of dust, this massive galaxy cluster remained invisible for decades. Yet its gravitational influence was undeniable, like a cosmic puppet master, pulling the strings of our entire cosmic neighborhood. Today, we're uncovering how astronomers finally pierced the cosmic veil to reveal this hidden giant, and why the Norma cluster holds the key to understanding the Great Attractor. Let's start with the basics. The Norma cluster, also known as ACO 3627, is one of the most massive galaxy clusters in our cosmic neighborhood. Located about 222 million light-years from Earth, it sits right in the heart of the Great Attractor region, that mysterious gravitational focal point pulling our Milky Way and thousands of other galaxies toward it. But for decades, the Norma cluster remained hidden from view, obscured by the thick clouds of interstellar dust in our own galaxy. The first hints of its existence came in the 1980s, when astronomers studying the motion of galaxies noticed something strange. Galaxies in the direction of the constellations Norma and Ara were moving faster than expected, as if being pulled by something massive. But when they pointed their telescopes in that direction, they saw nothing but the Milky Way's dust. It was like hearing a roar behind a closed door, but being unable to see what's making the sound. The breakthrough came with the development of new astronomical techniques that could see through dust. As we discussed in the previous chapter, infrared telescopes like IRAS and Spitzer were the first to reveal galaxies hidden behind the zone of avoidance. When astronomers pointed these infrared eyes toward the Norma region, they finally saw what was lurking there, a massive concentration of galaxies, glowing brightly in infrared light. But the real revelation came when X-ray telescopes joined the investigation. Galaxy clusters aren't just collections of galaxies, they're filled with incredibly hot gas, heated to millions of degrees by the immense gravity of the cluster. This superheated gas glows brightly in X-rays, invisible to our eyes, but detectable by special telescopes in space. When NASA's Chandra X-ray Observatory pointed toward the Norma cluster, what it saw was astonishing. The cluster was filled with vast clouds of superheated gas, extending millions of light years into space. This gas was so hot, tens of millions of degrees, that it was emitting X-rays powerful enough to penetrate the Milky Way's dust. For the first time, astronomers could see the full extent of the Norma cluster, and it was even more massive than they had imagined. The X-ray observations revealed something crucial about the Norma cluster's mass. The hot gas in the cluster is held in place by gravity. The cluster's total mass must be enormous to prevent this superheated gas from flying apart into space. By measuring the temperature and distribution of the gas, astronomers could calculate the total mass needed to contain it. What they found was staggering. The Norma cluster has a mass equivalent to about 10,000 Milky Way galaxies. That's 10 quadrillion times the mass of our Sun. A 1 followed by 16 zeros. But here's where it gets really interesting. When astronomers added up all the visible mass in the Norma cluster, the galaxies, the hot gas, everything they could see, It still wasn't enough to explain the gravitational pull they were measuring. There had to be something else. Something invisible but incredibly massive. That something is dark matter. Dark matter is the mysterious, invisible stuff that makes up about 27% of the universe. We can't see it directly, but we know it's there because of its gravitational effects. In galaxy clusters like Norma, dark matter forms a vast halo extending far beyond the visible galaxies and gas. This dark matter halo is what gives the cluster its enormous gravitational pull, affecting the motion of galaxies hundreds of millions of light years away. The Norma cluster's dark matter halo is so massive that it bends light from objects behind it, a phenomenon called gravitational lensing. By carefully studying how light from distant galaxies is distorted as it passes near the Norma cluster, astronomers can map the distribution of dark matter within it. What they've found is a complex web of dark matter filaments connecting the galaxies within the cluster, creating a gravitational network so powerful it influences everything around it. But what makes the Norma cluster so special? Why is it so important to understanding the Great Attractor? The answer lies in its position and motion. The Norma cluster sits near the center of the Great Attractor region, acting like its gravitational heart. It's the most massive cluster in this area, and its gravity dominates the motion of everything around it. Astronomers have measured the Norma cluster's peculiar velocity, its motion beyond the simple expansion of the universe. What they found is that the cluster is moving at about 600 kilometers per second toward the same general direction as our Milky Way and the rest of the local group. This coordinated motion suggests that both the Norma cluster and our local group are being pulled by something even more massive, something beyond the Norma cluster itself. That something is the Great Attractor. The Norma cluster isn't the Great Attractor itself, but rather the most visible component of it. The Great Attractor is a vast region of space where multiple dark matter filaments converge, creating a gravitational well so deep that it pulls in galaxies from hundreds of millions of light years around. The Norma cluster sits at the center of this well, like the heaviest marble in a bowl. But it's the bowl itself, the entire gravitational structure, that's the Great Attractor. The discovery of the Norma cluster was a crucial piece of the Great Attractor puzzle. Before its discovery, astronomers had detected the gravitational influence of the Great Attractor, but couldn't see what was causing it. The Norma cluster provided the first visible evidence of the massive structure lurking behind the zone of avoidance. It was like finding the first footprint of the invisible giant. But the Norma cluster is more than just evidence. It's a key to understanding the larger structure of the universe. By studying its properties, astronomers can learn about the formation and evolution of galaxy clusters, the distribution of dark matter, and the nature of the Great Attractor itself. One of the most fascinating aspects of the Norma cluster is its dynamic nature. Galaxy clusters aren't static objects. They're constantly evolving, growing by merging with other clusters and groups of galaxies. The Norma cluster is no exception. Astronomers have found evidence that it's currently merging with another, smaller cluster. This merger is creating shockwaves in the hot gas, heating it to even higher temperatures and triggering bursts of star formation in the galaxies involved. This merger process is crucial to understanding how the Norma cluster, and by extension, the Great Attractor, grew so massive. Over billions of years, the Norma cluster has consumed smaller clusters and groups, growing larger and more massive with each merger. Each merger adds not just galaxies and gas, but also dark matter, increasing the cluster's gravitational influence. The Norma cluster is also important because it's relatively close to us, at least in cosmic terms. At 222 million light-years away, it's close enough that astronomers can study it in detail. They can map the distribution of galaxies within it, measure the temperature and density of its hot gas, and trace the dark matter filaments connecting everything together. This detailed view provides insights into how all galaxy clusters work, not just the Norma cluster. But studying the Norma cluster is still challenging. Even with modern telescopes, the Milky Way's dust partially obscures our view. Astronomers have to use every tool at their disposal: infrared telescopes to see through the dust, X-ray telescopes to map the hot gas, radio telescopes to detect neutral hydrogen, and gravitational lensing to trace the dark matter. Each technique provides a different piece of the puzzle, and only by combining them can astronomers get a complete picture of the cluster. One of the most powerful tools for studying the Norma cluster has been the Atacama Large Millimeter / Submillimeter Array, ALMA, in Chile. ALMA is a collection of 66 radio telescopes working together as one giant telescope. It's particularly good at detecting cold gas and dust, making it ideal for studying the Norma cluster and other objects behind the Milky Way's dust. With ALMA, astronomers have mapped the distribution of molecular gas in the Norma cluster's galaxies. This gas is the raw material for star formation, and by studying how it's distributed, astronomers can understand how the cluster's environment affects the evolution of its galaxies. What they've found is that galaxies in the Norma cluster have less gas than similar galaxies outside clusters, suggesting that the cluster environment is stripping gas from the galaxies, quenching their star formation. This process, called ram pressure stripping, happens when galaxies move through the hot gas in the cluster. The hot gas acts like a cosmic wind, stripping the colder gas from the galaxies as they pass. Without this cold gas, the galaxies can't form new stars, so they slowly fade and die. It's like watching a cosmic predator devouring its prey. The Norma cluster is also a laboratory for studying dark matter. By mapping the distribution of galaxies, hot gas, and dark matter within the cluster, astronomers can test theories about how dark matter behaves. Does it interact with normal matter? Does it interact with itself? The answers to these questions have profound implications for our understanding of the universe. One of the most surprising discoveries about the Norma cluster came from studying its galaxies' motions. Astronomers expected the galaxies to be moving randomly within the cluster, like bees in a hive. But what they found was that many of the galaxies are moving in coordinated patterns, as if following invisible highways through the cluster. These patterns suggest that the dark matter in the cluster isn't smoothly distributed, but forms a complex web of filaments and streams that guide the galaxy's motion. This discovery has important implications for the Great Attractor as a whole. If the Norma cluster's dark matter is arranged in such a complex web, then the larger Great Attractor structure might be even more intricate than we thought. It's not just a simple gravitational well, but a complex network of dark matter filaments, each pulling galaxies in different directions, all converging toward the center. The Norma cluster also provides clues about the future of our own local group. As we discussed earlier, the local group is being pulled toward the Great Attractor at about 600 kilometers per second. In about 100 billion years, the local group will merge with the Virgo cluster, and eventually, this combined structure will merge with the Norma cluster and the rest of the Great Attractor region. It's a cosmic reunion billions of years in the making. But perhaps the most profound aspect of the Norma cluster is what it tells us about our place in the universe. We're not just floating in empty space. We're part of a vast, dynamic structure, a cosmic tapestry woven from the threads of gravity, dark matter, and galaxy motions. The Norma cluster is a crucial part of this tapestry, a massive node where multiple cosmic flows converge, and our Milky Way is caught in this flow, being pulled toward the Norma cluster and the larger Great Attractor beyond it. The discovery and study of the Norma cluster is a testament to human curiosity and ingenuity. For decades, this massive structure remained hidden behind the Milky Way's dust, its presence only betrayed by its gravitational influence. But astronomers refused to accept this limitation. They developed new tools, new techniques, new ways of seeing the universe, and finally, they pierced the cosmic veil to reveal the hidden giant. The story of the Norma cluster is far from over. Each new observation reveals new details, new complexities, new mysteries. Future telescopes, like the James Webb Space Telescope and the Square Kilometre Array, will provide even more detailed views, allowing us to study the cluster's galaxies, map its dark matter distribution, and understand its role in the larger Great Attractor structure. What we've learned so far is that the Norma cluster is more than just a collection of galaxies. It's a gravitational powerhouse, a cosmic laboratory, a key to understanding the Great Attractor and the large-scale structure of the universe. It's a reminder that the universe is full of hidden wonders, waiting to be discovered by those curious enough to look. As we continue to study the Norma cluster and the Great Attractor, we're not just learning about distant objects in space. We're learning about the fundamental forces that shape our universe, about the mysterious dark matter that makes up most of it, and about our own place in the cosmic tapestry. We're uncovering the hidden architecture of everything, one galaxy cluster at a time. If you want to discover how radio astronomy is providing even more details about the Norma cluster and revealing structures that even infrared and X-ray telescopes can't see, watch our next video, where we explore how radio waves are piercing the cosmic veil in a whole new way. Imagine you're trying to solve a mystery in a pitch-black room. You can't see anything, but you have special tools. One that detects heat signatures, and another that picks up radio signals. Suddenly, the room comes alive with invisible patterns and hidden connections. That's exactly what astronomers face when studying the Great Attractor. They're exploring a region hidden by the Milky Way's dust, but they've developed extraordinary ways to see what's invisible to our eyes. Today, we're uncovering how X-ray and radio astronomy became our cosmic super senses, revealing the hidden matter and structures that make the Great Attractor one of the universe's greatest mysteries. Let's start with X-ray astronomy. While infrared light can penetrate dust, X-rays take it a step further. They can actually tell us about the hottest, most energetic processes in the universe. Galaxy clusters like the Norma cluster we discussed earlier are filled with incredibly hot gas, heated to millions of degrees by the immense gravity of the cluster. This superheated gas glows brightly in X-rays, creating a cosmic fingerprint that even the thickest dust can't hide. NASA's Chandra X-ray Observatory has been our most powerful eye in the X-ray universe. When Chandra pointed toward the Great Attractor region, what it saw was breathtaking. Vast clouds of superheated gas extending millions of light years into space, all glowing in X-rays. This gas is so hot, tens of millions of degrees, that it's actually brighter in X-rays than in any other wavelength. It's like seeing the glowing embers of a cosmic fire that's been burning for billions of years. But here's where it gets really interesting. This hot gas is held in place by gravity. The cluster's total mass must be enormous to prevent this superheated gas from simply flying apart into space. By measuring the temperature and distribution of the gas, astronomers can calculate exactly how much mass is needed to contain it. And what they found in the Great Attractor region was staggering. There's far more mass than can be accounted for by visible matter alone. This is where dark matter comes in. The X-ray observations revealed that galaxy clusters in the Great Attractor region are embedded in massive halos of dark matter. This dark matter doesn't emit X-rays itself, but its gravitational influence shapes the distribution of the hot gas. By studying how the gas is distributed and how it moves, astronomers can map the dark matter with incredible precision. It's like seeing the shadow of an invisible giant. You can't see the giant itself, but you can see how it affects everything around it. X-ray observations have also revealed something crucial about the dynamics of the Great Attractor. The hot gas in galaxy clusters isn't static. It's constantly churning and flowing, creating shock waves and turbulence. By studying these motions, astronomers can understand how galaxy clusters grow and evolve. They've found that clusters in the Great Attractor region are actively merging with each other, creating even larger structures over time. It's like watching a cosmic demolition derby, where the collisions build something bigger instead of tearing things apart. But X-rays aren't the only tool in our cosmic toolkit. Radio astronomy has been equally revolutionary in studying the Great Attractor. While X-rays reveal the hottest gas, radio waves can detect something completely different: neutral hydrogen gas. This is the raw material for star formation, and it emits a specific radio wavelength called the 21 centimeter line. The 21 centimeter line is like a cosmic barcode for hydrogen gas. By mapping this radio signal, astronomers can trace the distribution of hydrogen gas across the universe, even through the Milky Way's dust. Radio waves pass through dust clouds unimpeded, making them perfect for studying the zone of avoidance. One of the most important radio surveys for the Great Attractor has been the Parkes HY All-Sky Survey. Using the iconic Parkes radio telescope in Australia, the same one featured in the movie The Dish, astronomers mapped the distribution of hydrogen gas across the entire southern sky, including the previously hidden Great Attractor region. What they found was a complex network of hydrogen filaments connecting galaxy clusters and superclusters, all flowing toward the gravitational center of the Great Attractor. But radio astronomy reveals more than just hydrogen gas. It can also detect synchrotron radiation, radio waves emitted by high-energy electrons spiraling around magnetic fields. This radiation is particularly common in galaxy clusters, where turbulence and shock waves accelerate electrons to near light speeds. By mapping this radio emission, astronomers can study the magnetic fields and energetic processes within clusters, providing another window into the hidden dynamics of the Great Attractor. The combination of X-ray and radio observations has been incredibly powerful. While X-rays reveal the hot gas and dark matter distribution, radio waves map the cooler hydrogen gas and magnetic fields. Together, they provide a complete picture of the visible and invisible matter in the Great Attractor region. One of the most exciting developments in radio astronomy is the Square Kilometre Array, SKA, currently under construction in Australia and South Africa. When completed, the SKA will be the most powerful radio telescope ever built, with a collecting area of 1 square kilometre. It will be able to map the 21 centimetre hydrogen line with unprecedented sensitivity and resolution, revealing the large-scale structure of the universe in exquisite detail. For the Great Attractor specifically, the SKA will allow astronomers to map the distribution and motion of hydrogen gas in 3 dimensions, tracing the cosmic flows that converge toward the gravitational center. It will be able to detect faint radio signals from distant galaxies hidden behind the Milky Way's dust, potentially revealing new structures in the Great Attractor region that we've never seen before. But radio astronomy isn't just about mapping gas. It's also about precision measurements of distances and motions. By using a technique called Very Long Baseline Interferometry, VLBI, which links multiple radio telescopes across continents or even around the world, astronomers can measure the positions and motions of objects with incredible accuracy. This has been crucial for determining the peculiar velocities of galaxies in the Great Attractor region, their motion beyond the simple expansion of the universe. What makes these X-ray and radio observations so remarkable is how they complement each other. X-rays show us the hot, energetic processes, the superheated gas, the dark matter halos, the merging clusters. Radio waves reveal the cooler gas, the magnetic fields, the large-scale structure. Together, they provide a complete picture of the Great Attractor that no single wavelength could achieve on its own. One of the most surprising discoveries from combining these observations is that the Great Attractor isn't a single, monolithic structure. Instead, it's a complex network of interconnected filaments and nodes, each with its own dynamics and evolution. Some regions are actively forming stars, others are dominated by old stellar populations. Some clusters are merging, others are relatively quiet. It's like discovering that what you thought was a single mountain is actually an entire mountain range, with its own valleys, peaks, and ecosystems. This complexity has important implications for our understanding of how large-scale structures form in the universe. The Great Attractor isn't just some local anomaly. It's a prime example of how the cosmic web evolves over billions of years. By studying it in detail, astronomers can test their theories of structure formation, dark matter, and the fundamental forces that shape our universe. But perhaps the most profound aspect of these X-ray and radio observations is what they reveal about the nature of discovery itself. The Great Attractor remained hidden for so long because we were limited to visible light. But by developing new ways to see the universe, new senses that can detect X-rays and radio waves, we've revealed an entirely new cosmic landscape. It's a reminder that the universe is full of wonders waiting to be discovered by those curious enough to look in new ways. The technology behind these observations is just as remarkable as the discoveries. X-ray telescopes like Chandra use nested mirrors that barely graze incoming X-rays, focusing them onto detectors with incredible precision. Radio telescopes like the SKA use advanced signal processing to combine signals from multiple antennas, creating virtual telescopes the size of entire continents. These are marvels of human ingenuity, pushing the boundaries of what's possible. And the story isn't over yet. Future X-ray missions, like the proposed Lynx X-ray Observatory, will be even more powerful than Chandra, with the ability to map the hot gas in galaxy clusters with unprecedented detail. Next-generation radio telescopes, like the SKA, will reveal the large-scale structure of the universe in 3 dimensions, tracing the cosmic web from the Great Attractor to the most distant reaches of space. What we've learned so far from X-ray and radio astronomy is that the Great Attractor is more than just a gravitational anomaly. It's a complex, dynamic system that's been evolving for billions of years. It's a laboratory for studying the fundamental forces that shape our universe, and it's a reminder that there's still so much we don't know about the cosmos. As we continue to study the Great Attractor with these powerful tools, we're not just mapping distant objects in space. We're uncovering the hidden architecture of the universe, tracing the invisible threads of dark matter and energy that connect everything. We're solving a cosmic mystery that began with a simple question: why are galaxies moving where they're moving? And with each new observation, we're getting closer to the answer. If you want to discover how all these different observations, infrared, X-ray, radio, and more, are being combined to create the most complete picture ever of the Great Attractor, watch our next video, where we explore how modern astronomy is weaving together multiple wavelengths to reveal the hidden universe. Imagine you're watching a spider build its web. You can't see the silk being spun, but suddenly there it is, an intricate pattern connecting everything together. That's exactly what dark matter does in our universe. It's the invisible framework holding everything together, the cosmic scaffolding that shapes where galaxies form and how they move. Today, we're uncovering how astronomers have pieced together the evidence for this mysterious substance, and why the Great Attractor is giving us our best clues yet about what dark matter really is. Let's start with a simple question. What is dark matter? Despite its name, dark matter isn't dark in the way a room without lights is dark. It's transparent. It doesn't emit, reflect, or absorb any light at all. We can't see it with any telescope, no matter how powerful. So how do we know it exists? The answer is in its gravity. Dark matter has mass, which means it has gravity, and that gravity affects everything around it. Think of it like this. Imagine you're watching a parade. You can't see the people pushing the floats from behind, but you can see how the floats move, how they turn, how they speed up or slow down. By watching the floats, you can figure out where the invisible pushers are. That's exactly what astronomers do with dark matter. They watch how galaxies and galaxy clusters move, and from those motions, they can map where the dark matter must be. The first hints of dark matter came in the 1930s, when astronomer Fritz Zwicky was studying the Coma cluster of galaxies. He measured how fast the galaxies in the cluster were moving, and found something strange. They were moving so fast that the cluster should have flown apart. There wasn't enough visible matter to hold it together with gravity. Zwicky suggested there must be some invisible dark matter, providing the extra gravity needed to keep the cluster intact. At the time, few people believed him. Fast forward to the 1970s, when astronomer Vera Rubin was studying spiral galaxies. She measured how fast stars were orbiting around the centers of these galaxies. According to our understanding of gravity, stars farther from the center should be moving slower, just like planets farther from the sun orbit more slowly. But Rubin found that the stars at the edges of galaxies were moving just as fast as those near the center. This was impossible unless there was a lot more mass in these galaxies than we could see, mass in the form of dark matter. These early discoveries were just the beginning. Today, we have overwhelming evidence that dark matter makes up about 27% of the universe, far more than the 5% that's normal matter, the stuff we can see. The remaining 68% is dark energy, an even more mysterious force that's causing the expansion of the universe to accelerate. But how does this relate to the Great Attractor? The Great Attractor is essentially a massive concentration of dark matter. All the galaxy clusters and superclusters we see in that region, like the Norma cluster we discussed earlier, are just the tip of the iceberg. The real mass is in the dark matter halo surrounding them. When astronomers mapped the motion of galaxies toward the Great Attractor, they were essentially mapping the gravitational influence of this dark matter concentration. The galaxies are like leaves floating on a river. They follow the currents created by the underwater landscape. In this case, the underwater landscape is the distribution of dark matter. One of the most powerful tools for mapping dark matter is gravitational lensing, which we touched on earlier. When light from a distant galaxy passes near a massive object, the gravity of that object bends the light's path, distorting the galaxy's image. By studying these distortions, astronomers can map exactly where the mass is, even if that mass is completely dark. For the Great Attractor specifically, gravitational lensing has revealed vast clouds of dark matter extending far beyond the visible galaxy clusters. These dark matter halos are enormous, stretching millions of light years into space. What's more, they're not just random blobs. They're connected by long filaments of dark matter, forming a cosmic web that spans the entire universe. This cosmic web is perhaps the most remarkable discovery in modern cosmology. The universe isn't just a random scattering of galaxies. It's an intricate network of filaments and nodes, with vast voids in between. The galaxies we see form along these filaments, like dewdrops on a spiderweb, and the entire structure is held together by dark matter. Computer simulations have been crucial for understanding this cosmic web. The Millennium simulation, which we mentioned earlier, modeled over 10 billion particles of dark matter evolving over billions of years. The results were stunning. A cosmic web strikingly similar to what astronomers observe in the real universe. These simulations show how dark matter collapses under gravity to form filaments and nodes, with galaxies forming at the intersections of these filaments. For the Great Attractor, these simulations show that it's not just a single concentration of dark matter. It's a complex network where multiple dark matter filaments converge, creating a gravitational well so deep that it pulls in galaxies from hundreds of millions of light years around. The visible galaxy clusters in the region, like the Norma cluster, are just the brightest nodes in this network, the places where the filaments intersect and matter is most concentrated. But how do we know that dark matter isn't just normal matter that we can't see? Maybe it's just a lot of faint stars, or black holes, or dust clouds that don't emit light. Astronomers have considered these possibilities, but they've been ruled out by several lines of evidence. First, there's the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation is incredibly uniform across the sky, but it has tiny temperature fluctuations. These fluctuations correspond to density variations in the early universe. By mapping these fluctuations with satellites like Planck, astronomers can calculate how much normal matter and dark matter there must be to create the patterns we see. The results match perfectly with the idea that dark matter is a separate, invisible substance. Second, there's the evidence from Big Bang nucleosynthesis, the process that created the first atomic nuclei in the early universe. The amounts of different elements like hydrogen, helium, and lithium that we observe today match what we'd expect if only about 5% of the universe is normal matter. If there were much more normal matter in the form of faint stars or black holes, it would have changed these element abundances. Third, there's the evidence from galaxy collisions. When galaxy clusters collide, the normal matter, in the form of hot gas, slows down due to friction. But the dark matter, which doesn't interact with gas, keeps moving at high speed. The bullet cluster is the most famous example of this. When astronomers mapped the mass distribution in the bullet cluster, they found that most of the mass was in two separate clumps, offset from the visible galaxies and gas. This is exactly what you'd expect if dark matter exists and behaves differently from normal matter. All these lines of evidence point to the same conclusion. Dark matter is real. It's not made of normal matter, and it makes up about 27% of the universe. And it's this dark matter that shapes the large-scale structure of the universe, including the Great Attractor. But what is dark matter made of? That's where things get really mysterious. We know it's not normal matter, not stars, not planets, not dust. The leading candidates are exotic particles that we haven't discovered yet. One possibility is WIMPs, weakly interacting massive particles. These would be heavy particles that interact only through gravity and the weak nuclear force, making them very difficult to detect. Another possibility is axions, extremely light particles that were originally proposed to solve a different problem in particle physics, but could also explain dark matter. Scientists around the world are building experiments to detect these particles directly. Deep underground laboratories, like the Large Underground Xenon LUX experiment and the XENON1T experiment, are trying to detect WIMPs by looking for the rare interactions they might have with normal matter. Other experiments are searching for axions using strong magnetic fields. So far, no definitive detections, but the search continues. For the Great Attractor specifically, understanding dark matter is crucial. The Great Attractor is essentially a massive node in the cosmic web, a place where multiple dark matter filaments converge. The visible galaxy clusters in the region are just tracers, revealing the location of this dark matter concentration. By studying the Great Attractor, astronomers can learn about the properties of dark matter and how it shapes the universe. One of the most exciting recent developments is the use of machine learning to map dark matter. Astronomers are training artificial intelligence systems to recognize the patterns in galaxy distributions that reveal the underlying dark matter. These AI systems can analyze vast amounts of data from galaxy surveys and create detailed maps of the dark matter distribution for the Great Attractor region. These maps are revealing a complex network of filaments and nodes, with the Great Attractor at the center of it all. But perhaps the most profound aspect of dark matter is what it tells us about our place in the universe. We're made of normal matter, the stuff that's just a small fraction of everything that exists. The vast majority of the universe is made of something we can't see, something we don't fully understand. It's a humbling reminder of how much we still have to learn about the cosmos. The Great Attractor is a perfect example of this mystery. It's one of the largest structures in our cosmic neighborhood, yet most of it is invisible. We can't see it directly, but we can see its effects: the motion of galaxies, the bending of light, the distribution of hot gas. These effects reveal the presence of something massive, something invisible, something that shapes the very fabric of the universe. As we continue to study the Great Attractor and dark matter, we're not just learning about distant objects in space. We're uncovering the fundamental nature of reality itself. We're exploring the invisible forces that shape everything, from the smallest particles to the largest structures in the universe. And in doing so, We're pushing the boundaries of human knowledge, one discovery at a time. If you want to discover how all these pieces of the puzzle, dark matter, galaxy motions, cosmic structure, and the great attractor, are coming together to revolutionize our understanding of the universe, watch our next video, where we explore the latest breakthroughs in solving the mystery of the great attractor. Imagine trying to draw a portrait of someone you've never seen. You only have clues, the way people move when they're near them, the shadows they cast, the footprints they leave in the sand. That's exactly what astronomers faced with the great attractor. For decades, they knew something massive was lurking behind the Milky Way's dust, pulling galaxies across hundreds of millions of light years, but they couldn't see it directly. Today, we're uncovering how scientists finally pieced together the first rough portrait of this cosmic giant. A portrait drawn not with light, but with gravity, motion, and invisible forces. Let's start with the big picture. After decades of observations across multiple wavelengths, infrared, X-ray, radio, and more, astronomers finally had enough data to connect the dots. The great attractor wasn't a single object like a supermassive black hole or a giant galaxy cluster. It was something far more complex and fascinating. A vast gravitational focal point where multiple cosmic structures converge. The first breakthrough came from combining all those peculiar velocity measurements we discussed earlier. Astronomers had been tracking how thousands of galaxies move through space, beyond the simple expansion of the universe. When they mapped all these motions together, a clear pattern emerged. Galaxies weren't moving randomly. They were flowing like rivers, all converging toward the same general region in the direction of the constellations Centaurus and Hydra. But here's where it got interesting. This flow wasn't uniform. Galaxies closer to the great attractor region were moving faster than those farther away, exactly as you'd expect if they were being pulled by a massive gravitational source. It was like watching water flow toward a drain. The closer the water, the faster it moves. The next piece of the puzzle came from infrared observations. Telescopes like Spitzer and WISE had peered through the Milky Way's dust and revealed a complex network of galaxies and galaxy clusters hidden behind it. When astronomers overlaid these infrared maps with the peculiar velocity maps, they found something astonishing. The galaxies weren't just randomly distributed behind the dust. They were arranged in vast filaments and sheets, all pointing toward the same gravitational center. But the real revelation came when astronomers put all these observations together into a single 3D model. What emerged was a portrait of the great attractor, unlike anything they had imagined. It wasn't a single object, or even a single cluster. It was a vast region of space, where multiple dark matter filaments converge, creating a gravitational well so deep that it pulls in galaxies from all directions.